Welcome to the Deep Dive. Today, we're going deep into, well, a fascinating area of mathematics, control theory. We're looking at a research paper. It's called Controllability for a 2x2 nonlinear degenerate parabolic system via one boundary control force.
Quite a mouthful.
Yeah.
But
Yeah.
I know it's the title actually gives us a lot of information about the problem. We're basically trying to figure out, can we control a system described by, well, two equations that are interconnected, and we're only allowed to kind of like manipulate it at a certain point on its boundary.
Okay. I'm intrigued already. So it's kind of like, trying to steer a ship with just a tiny rudder, right? But what makes these equations so special? The title mentions degenerate. What does that even mean in this context?
Yeah, so degenerate, it refers to the fact that the equation's behavior can change quite drastically depending on where you are in the system. Imagine like a heat source that spreads heat differently depending on the material that it's in. That's kind of the idea.
Got it. So we've got this complex system. We're trying to control it with limited tools. How did the researchers even begin to approach this problem?
Well, the first step is to determine, is the system even controllable in the first place? And that's where Kalman's rank condition comes in. It's a mathematical test that tells us, do we even have a chance of steering the system to a desired state? Think of it as checking if your rudder is actually connected to the ship's steering mechanism.
Okay, that makes sense. So it's a necessary condition for controllability, but not necessarily sufficient, right?
Exactly. So passing this test means that we can potentially control the system, but it doesn't tell us how. So the researchers then delve into the specifics of the system itself, and these equations are nonlinear, which makes the problem much harder to solve compared to linear systems. To simplify things, they first analyze a related linear system.
Right, it's a common strategy in mathematics. Break down a complex problem into smaller, more manageable pieces. So they're looking at the linear system to gain insights into the nonlinear one.
Precisely. And they use a clever trick to simplify things further. They introduce a change of variables that transforms the system into a specific form, where the control matrix, denoted by B, is simply 1, 0. This makes the equations much easier to work with.
So they're essentially cleaning up the equations to make them, more presentable, kind of like organizing a messy toolbox.
Yes. And this transformation leads to a system where the coupling matrix, A, which describes how the two equations are linked, has a specific form with elements 0, A1, 1, and A2.
Okay. So they've streamlined the equations. What's the next step in their mathematical journey?
They bring in a powerful tool from the world of mathematical functions, Bessel functions.
Bessel functions. Now, Bessel functions ring a bell. Aren't they solutions to a specific type of differential equation?
Yes, they are solutions to Bessel's differential equation, which is a second-order equation that appears in various areas of physics and engineering. These functions have a unique oscillatory behavior, kind of like a wave that gradually decays. And they have infinitely many points where they cross the x-axis, which we call zeros.
Okay, so they're not your typical everyday functions. How do these Bessel functions help with the controllability problem?
Well, the researchers use them to analyze the system's eigenvalues and eigenfunctions. Eigenvalues are, like the system's resonant frequencies. They tell us how the system evolves over time. Eigenfunctions are the corresponding patterns associated with those frequencies, capturing the system's spatial behavior.
So it's like finding the unique set of notes that make this mathematical instrument resonate.
That's a fantastic analogy. And by understanding these eigenvalues and eigenfunctions, the researchers can gain deeper insights into the system's dynamics. They leverage some known properties of Bessel functions, such as bounds on their zeros, to analyze the spectrum of the system, which is essentially the collection of all possible eigenvalues.
So they're digging into the mathematical DNA of the system to understand its fundamental properties. And what did they discover?
They found that the eigenvalues are given by a specific formula involving the squares of scaled Bessel function zeros minus certain values determined by the coupling matrix A. The eigenfunctions, in turn, are expressed in terms of these scaled Bessel functions.
Okay, so we're getting into some heavy math here. But why is all of this so important for the control problem?
Well, they've found a crucial property of the eigenvalues. They satisfy what's called a gap condition. This means that there's a minimum distance between any two eigenvalues, kind of like ensuring that the notes of our mathematical instrument aren't too close together.
Interesting. So not only do the specific values of the eigenvalues matter, but their spacing also plays a role.
Exactly. This gap condition, along with the convergence of a specific series involving the eigenvalues, lays the groundwork for a powerful technique used to solve controllability problems, the moment method.
Okay. So they've carefully analyzed the Bessel function properties
Yeah.
and the system spectrum. Now they're bringing in the big guns, the moment method. But before we get into that, I think we need to take a deeper look at these vectorial operators they introduce.
Absolutely. Those are key to the next stage of the analysis, but let's save that for the next part of our deep dive. Welcome back. We left off talking about how the researchers analyzed the system's eigenvalues and eigenfunctions using Bessel functions. Now we're going to see how those building blocks are used to construct a more powerful framework with vectorial operators.
Okay, I remember you mentioned these operators, L and L, but I'm still a bit fuzzy on what they represent and why they're so important.
Right. So let's break it down. Remember how we started with a system of two interconnected equations? These vectorial operators are essentially matrix generalizations of the scalar operators that were implicitly present in those equations. They capture the system's behavior in a more compact and general way.
So it's like upgrading from a basic wrench to a multi-tool. They can handle more complex tasks.
Exactly. The researchers analyzed the spectra of these vectorial operators, which, as you might expect, are closely related to the spectra of the corresponding scalar operators we discussed earlier. And guess what? They discovered that the spectra of L and L are determined by the eigenvalues of that coupling matrix A, specifically the expression A22 plus 4A1.
That expression again, it seems to be popping up everywhere. So the specific values within the coupling matrix A, which describes how the two equations are linked, really dictate the system's overall behavior.
Absolutely. And depending on whether A22 plus 4A1 is positive or negative, they obtain two distinct cases for the eigenvalues of L and L. For each eigenvalue, they also provide explicit expressions for the corresponding eigenfunctions of L and L. These eigenfunctions are expressed in terms of the scalar eigenfunctions we discussed earlier, combined with specific vectors derived from the coupling matrix A.
Sounds like they're meticulously piecing together the puzzle, building from scalar operators to vectorial operators and connecting everything back to the properties of the coupling matrix A. But where does the control part come in?
That's where things get really interesting. Remember the moment method we talked about earlier? Well, to effectively use that method, we need a special ingredient, bioorthogonal families.
Okay, bioorthogonal families. It's unfamiliar, but can you remind me what that means?
Numbers. Think of it like this. Imagine you have two sets of keys, and each key from one set only unlocks a specific lock from the other set. That's the basic idea behind bioorthogonality. In mathematical terms, two families of vectors are bioorthogonal if each vector from one family is orthogonal to all but one vector from the other family.
Okay, that analogy helps. But how do these bioorthogonal families help us control this complex system?
Well, the moment method basically transforms the controllability problem into a different kind of problem called a moment problem. This involves finding a function, our control function, that satisfies a set of integral equations. These integral equations are called moment equations because they involve integrals of the unknown function multiplied by specific known functions.
So it's like translating one mathematical language into another, and bioorthogonal families act as the dictionary.
Exactly. They provide the link between the solution of the moment problem and the solution of the original control problem.
I'm starting to see how all these pieces fit together. It's a fascinating interplay of different mathematical tools. But how do they actually find these bioorthogonal families?
The researchers highlight a specific family, denoted nyanan, which consists of all the eigenvalues of L, plus a constant term related to the eigenvalues of the coupling matrix A. This family satisfies the conditions of a powerful theorem that guarantees the existence of a bioorthogonal family.
So they've proven that the necessary ingredients for the moment method are in place.
Precisely. They go even further by proving that two specific sequences, B and B, constructed from the eigenfunctions of L and L, form bioorthogonal families in various function spaces. They also demonstrate that these families are complete, meaning they can represent any function in those spaces, and they form what are known as Riesz bases.
Well, on Riesz bases, what are those and why are they important?
Think of a Riesz basis as a set of building blocks that span the entire space while also being well-behaved in terms of their linear independence. It's a stronger condition than just being a basis. And it ensures that we can reliably reconstruct any function in the space using these basis vectors.
So these bioorthogonal Riesz bases are like a super stable foundation for representing functions in our system.
Exactly. It's like having a set of superglued Lego bricks. That won't fall apart when you build something complex. And this brings us to the heart of the matter, the moment method itself.
Okay, I'm eager to see how they actually apply this method to find the control function.
Right, and that's what we'll dive into next. The researchers used the moment method to transform the controllability problem into a problem of finding a function that satisfies certain integral conditions. It's a clever technique that leverages the properties of the biorthogonal families we just discussed.
Sounds like we're finally getting to the action.
We are. Let's continue this exciting journey in the next part of our deep dive.
Welcome back to the deep dive. We've been on quite a mathematical journey, exploring, Bessel functions, biorthogonal families, and all sorts of other fascinating concepts. Last we left off, we were about to see how the researchers actually use the moment method to find the control function. I'm all ears. Lay it on me.
Okay, so remember how we said that the moment method transforms the controllability problem into a problem of finding a function that satisfies certain integral conditions? Well, the researchers start by connecting the controllability of the system to its adjoint system.
Yeah.
The adjoint system is kind of like the mirror image of the original system. It helps us analyze the system from a different perspective.
So we're looking at the system's reflection to gain insights into how to control the original. That's pretty cool.
It is. The researchers show that the control function, denoted by V, can steer the original system to 0 at a specific time t. If and only if it satisfies a particular integral equation involving the solution of the adjoint system. This integral equation becomes the basis for the moment problem.
Okay, so we've got the moment problem set up. How do they actually solve it?
They use a clever combination of techniques. First, they express the solution of the adjoint system in terms of its eigenfunctions and complex exponentials. Remember those eigenfunctions we derived earlier using Bessel functions? Well, they come in handy here. The researchers then leverage the biorthogonality property of the eigenfunction families B and B to simplify the moment problem, reducing it to a set of equations involving coefficients related to the initial condition and the eigenfunctions.
So it's like they're breaking down a complex chord into its individual nodes, using those biorthogonal families as a guide.
That's a great analogy. They then perform a change of variables, substituting is for t to t to further simplify the moment problem. This transformation leads to a new set of moment equations, where the unknown function is now expressed in terms of is instead of if.
Okay, so they're doing some fancy mathematical gymnastics to make the equations more manageable. But do they actually find a solution for the control function?
They do. They propose a formal solution for the control function, which is expressed as an infinite series, involving the biorthogonal functions and coefficients derived from the moment equations.
Hold on, an infinite series. Doesn't that mean we need to add up infinitely many terms? How is that even possible?
It's a valid concern. But the researchers show that this infinite series actually converges, meaning that as you add more and more terms, the sum gets closer and closer to a specific value. They meticulously demonstrate that the control function they've derived is well-behaved and belongs to a special space of functions called L2OT. This space contains functions that are square integrable, which is a fancy way of saying that their energy is finite.
Got it. So they've shown that their solution is mathematically sound. But this was all for the linear system, right? How do they tackle the original nonlinear problem?
That's where things get even more ingenious. They employ a technique called the fixed point strategy. Imagine trying to hit a moving target. You need to constantly adjust your aim to account for its movement. That's kind of what the mathematicians are doing here. They're looking for a solution that stays put even though the system is constantly changing. They define an operator that maps a source term to the solution of the nonlinear system. The goal is to prove that this operator has a fixed point, which would correspond to a solution of the original nonlinear system.
So they're looking for a mathematical bullseye, a solution that remains stable even when the target is moving.
Exactly. To do this, they introduce a space, denoted by h, which contains functions that decay sufficiently fast as time approaches t. They define the operator O that takes a source term and produces the solution of the nonlinear system with that source term. They then meticulously analyze the properties of this operator and the space h, aiming to show that O maps a specific subset within h back into itself.
So it's like saying if you start with an input that's close enough to 0, the output will also be close enough to 0.
Yes. That's a great way to think about it. They use the estimates they derived earlier for the linear system to show that O does indeed map a certain ball of radius O back into itself, provided it is chosen small enough. They also need to show that this operator O is a contraction, meaning that it brings points closer together when applied repeatedly. This contraction property is crucial for using a powerful tool called the Banach fixed point theorem.
Okay, so we've got this operator that maps a ball back into itself and brings points closer together. What does that tell us?
Well, those two properties, combined with the fact that the ball is a complete metric space, fulfill the conditions of the Banach fixed point theorem. This theorem guarantees that the operator O has a unique fixed point within that ball. This fixed point corresponds to a source term F, such that the solution of the nonlinear system with that source term equals F itself. In simpler terms, they found a self-consistent solution to the nonlinear system.
That's incredible. So by starting with the linear system, cleverly defining an operator, and applying this Banach fixed point theorem, they've tackled the controllability of the nonlinear system.
Precisely. They've shown that a solution exists and that it decays to zero as time approaches t, which means they've established the local exact controllability of the nonlinear system.
Wow, what an amazing journey. From Bessel functions to biorthogonal families to the Banach fixed point theorem, they've combined a whole toolbox of mathematical concepts to crack this problem.
It's a true testament to the power of mathematical ingenuity. And the researchers didn't stop there. They also included an appendix with proofs of some key propositions, providing further insights into the mathematical machinery at play.
Ah, yes, the appendix. The hidden treasure trove of mathematical details. What can we find in there?
Well, the appendix starts by proving proposition 2.2, which establishes that the solution to the non-homogeneous linear system exists, is unique, and has certain smoothness properties. The proof uses a technique called the transposition method, which is a clever way to analyze solutions to partial differential equations with complicated boundary conditions. They introduce a special functional and apply the Riesz representation theorem to show that the solution exists and has the desired properties.
So they're really dotting their I's and crossing their T's, making sure every detail is rigorously proven.
Exactly. They also provide proofs for propositions 3.2 and 3.4, which delve deeper into the spectral properties of those vectorial operators L and L. These proofs demonstrate how the eigenvalues and eigenfunctions of L and L are directly related to the properties of the coupling matrix A, and those scalar eigenfunctions we derived earlier using Bessel functions. They show that the families B and B, constructed from the eigenfunctions of L and L, are biorthogonal, complete, and form Riesz bases, solidifying their role as a robust foundation for representing functions in the system.
It's fascinating how they've built this intricate mathematical framework, piece by piece, proving every step along the way.
It's a beautiful example of how mathematical rigor and creativity can work hand in hand.
I couldn't agree more. So we've reached the end of our deep dive into this fascinating research paper. We've explored a world of complex equations, clever techniques, and surprising connections. What are your final thoughts on this mathematical adventure?
I'm truly impressed by the researchers' ingenuity and the elegance of their solution.
Sure.
This paper is a testament to the power of mathematical tools and the importance of persistent exploration. It leaves me wondering, what other complex systems might be tamed using similar techniques?
That's a great question to ponder. And it's what the deep dive is all about, sparking curiosity and leaving you with more questions than answers. Thanks for joining us on this exciting mathematical journey. Welcome to the deep dive. Today we're diving into a fascinating area of advanced mathematics.
Oh, okay.
Yeah, the controllability of a 2x2 nonlinear degenerate parabolic system.
Okay.
We'll unpack the intricacies of this research,
Right.
exploring how a system described by these specific equations can be steered to a desired state using just one control input.
It's a pretty challenging problem and has real-world implications, especially in fields like engineering and physics.
Wow.
You can imagine trying to manipulate a complex machine with a single lever.
Oh, interesting.
That's the kind of control problem that we're dealing with here.
That's a great analogy.
Yeah.
We're going to dissect a research paper that tackles this problem using some really powerful mathematical tools.
Yes.
Including the moment method and a deep understanding of eigenvalues, eigenfunctions, and biorthogonal families.
That's right. And what makes this research even more intriguing is that the success of the control strategy really hinges on this delicate balance of conditions. We'll see how the structure of the equations, particularly the coupling matrix and the placement of the control input, play crucial roles in determining whether the system is controllable or not.
Sounds like a pretty fascinating challenge.
It is.
Let's dive right in.
Okay.
The paper kicks off by introducing the star of the show, a 2x2 nonlinear degenerate parabolic system.
All right.
Can you walk us through what that actually means?
Sure. These systems are described by partial differential equations, and they show up in a surprising number of places, from modeling heat flow and chemical reactions to even describing population dynamics.
Huh?
The degenerate part means that the usual smoothing effects of diffusion, which you often see in these types of systems, can actually disappear in certain regions, and this makes them trickier to analyze and control.
Okay, so it's like having a system where the usual rules don't always apply, making it more unpredictable.
Exactly. And the authors are specifically interested in controlling these systems using a single input applied only at the boundary of the system's domain. They call this boundary control.
So imagine trying to control the temperature of a room by manipulating the heat source only at one wall.
Right.
That's boundary control in action.
Exactly.
Now the researchers want to figure out if they can steer this entire system to a specific desired state using only this boundary control input despite the degeneracy.
That's right.
And that's the crux of the research question, right?
Yes.
Can they achieve this precise control with just one input, even when the system behaves in this unusual degenerate way?
Yes. That's the core challenge.
Okay.
To tackle this, they begin by simplifying things, focusing on a linearized version of the more complex nonlinear system.
Right.
It's a common strategy in mathematics to break down a tough problem into smaller, more manageable pieces.
Makes sense. You wouldn't try to build a skyscraper without first understanding the principles of structural engineering.
Exactly. So they start by analyzing a specific linearized system.
Okay.
They use a condition called the Kalman rank condition to determine whether this simplified system is controllable. This condition essentially involves checking the rank of a matrix that captures the relationship between the variables in the system.
So it's like checking if we have enough independent controls to manipulate all the essential aspects of the system.
Precisely, if the Kalman rank condition is satisfied, it means we have a fighting chance of controlling the system with a single input.
Okay.
Now, to simplify things even further, the paper focuses on a particular case where this matrix has two distinct eigenvalues.
Okay.
Eigenvalues are these special values that provide crucial information about the system's behavior.
They're like fingerprints that reveal the unique characteristics of the system.
Now, this is where things get really interesting.
Okay.
They introduce Bessel functions, a family of special functions that pop up frequently in physics and engineering.
Bessel functions. I remember hearing about those in my engineering courses.
Yeah.
Didn't they have something to do with waves and oscillations?
Yes, you're right. They often describe wave propagation or the behavior of systems that involve vibrations or oscillations. In this research, Bessel functions play a crucial role in analyzing the degenerate diffusion operator in the system of equations.
Okay, so how do these Bessel functions connect to the controllability problem?
Right.
It seems like a bit of a jump from waves and oscillations to controlling a complex system.
Well, the connection lies in the zeros of the Bessel functions. These zeros, which are the points where the Bessel function crosses the x-axis, are directly related to the eigenvalues of the degenerate diffusion operator.
Okay.
And remember, eigenvalues give us insights into the system's natural frequencies and how quickly disturbances decay.
So understanding the zeros of these Bessel functions provides a key to unlocking the behavior of the system.
Exactly. The researchers delve deep into the spectrum of the degenerate diffusion operator, which is essentially the collection of all its eigenvalues.
Okay.
And what they find is that these eigenvalues derived from those Bessel function zeros have to satisfy a specific condition for the system to be controllable.
So not just any arrangement of eigenvalues will do.
Precisely, they have to meet a condition called the gap condition, which ensures enough spacing between the eigenvalues. Think of it like making sure there's enough room on a crowded dance floor for everyone to move freely.
Yeah.
If the eigenvalues are too close together, it becomes harder to control the system precisely.
Got it. So the spacing of these eigenvalues determined by those Bessel function zeros is crucial for controllability.
Absolutely. And the authors actually verify that this gap condition is met, bringing us a step closer to proving the controllability of the linearized system.
So they've laid the groundwork by analyzing the linearized system and establishing some crucial conditions.
Right.
What's the next step in their approach?
They introduce a powerful technique called the moment method to further analyze the controllability problem.
Moment method. Moment problem. Sounds intriguing.
It is.
Can you elaborate on those a bit?
Imagine trying to describe a complex object by capturing its different moments. The first moment might give you its center of mass. The second moment might tell you about its spread, and so on.
Got it.
In a similar way, the moment method breaks down the controllability problem into a set of integral equations,
Okay.
where each equation represents a moment of the system's behavior.
So instead of trying to control the system directly, they break it down into these moments, which are easier to handle mathematically.
Exactly. It's like analyzing a complex painting by focusing on its individual brushstrokes.
Okay.
By understanding each brushstroke, you gain a deeper appreciation of the entire artwork.
That's a great analogy. So they've transformed the problem into this moment problem, but how do they actually solve it?
This is where biorthogonal families enter the scene.
Biorthogonal families.
Yes. These are sets of functions that are carefully chosen to have specific orthogonality relationships.
Okay.
Think of them as specialized tools designed to unlock the solution to the moment problem.
So like having the right key for a specific lock?
Precisely the existence of a biorthogonal family, which the paper meticulously proves, is key to constructing a control function that solves the moment problem.
Okay, so they've laid the foundation with Bessel functions, established conditions for controllability, and transformed the problem using the moment method.
Right.
Now, with the help of biorthogonal families, they're ready to crack the code of the moment problem.
That's right.
I'm eager to see how they use these pieces to finally construct a control function for the system.
Me too. But first, we need to understand how they bridge the gap between the simplified linear system and the full nonlinear model. Shall we continue exploring?
Let's do. The deep dive is getting more and more fascinating with every step.
Okay. So as we were saying, the journey doesn't end with controlling just the simplified linear system. The paper dives into the controllability of a related system called the non-homogeneous system.
Okay, so what's different about this non-homogeneous system? What makes it special?
Well, the non-homogeneous system introduces a source term denoted by F into the equations. This term represents an external influence acting on the system, making its behavior more complex and unpredictable.
So it's like adding wind gusts to our car parking analogy. Suddenly there's an external force that can push the car off course, making our steering wheel control even more challenging.
Exactly. The source term can disrupt the system's dynamics, and the researchers need to figure out a way to overcome this additional challenge.
So how do they adapt their control strategy to handle this source term?
They use a clever technique that leverages the controllability of the homogeneous system, the one without the source term. Essentially, they break down the problem into smaller pieces, focusing on controlling the system over short time intervals.
So it's like dividing the parking task into smaller maneuvers, each designed to counteract the wind gusts as best as possible.
That's a great analogy. They carefully choose a sequence of time intervals and design control inputs for each interval, taking into account the influence of the source term.
Okay, that makes sense. But how do they actually calculate these control inputs? It seems like it would get pretty complicated with the source term constantly changing things.
It definitely gets more complex. They use a combination of estimates and iterative techniques to gradually refine the control input. The key is to choose the right mathematical framework to represent the source term and its influence.
And what kind of framework do they use?
They use a weighted Lebesgue space, which is a fancy way of saying they assign different weights or importance to the source term at different points in time. This allows them to capture the dynamic nature of the source term's influence.
So it's like paying more attention to the strongest wind gusts, as those will have the biggest impact on our parking maneuvers.
Precisely. By carefully choosing these weights, they can fine-tune their control strategy to effectively counteract the source term's disruptive effects.
I see. So they've broken down the problem, figured out how to adjust the control input in each time interval, and now they need to combine everything to achieve null controllability. What does that look like?
Remember those functions off and I we talked about earlier? They come back into play here. The researchers define new spaces, FV, H, R, and H, based on these functions. Think of them as tailored mathematical environments where we can study the controllability problem with the added source term.
So these spaces help them organize and understand the behavior of the system with the source term.
Exactly. They then go through a detailed construction process. They define sequences and solutions to auxiliary systems, carefully building up their control strategy step by step. They meticulously analyze the behavior of these systems, deriving estimates and proving inequalities along the way.
It sounds like a delicate balancing act, making sure everything works in harmony.
Absolutely. It's a testament to the author's mathematical prowess. They combine existing techniques in novel ways and rigorously prove that their approach leads to a controllable system. They even provide explicit bounds on the control function, essentially quantifying how much effort is needed to steer the system to zero.
It's impressive how they take this abstract mathematical concept and turn it into something concrete and measurable.
Yes. And that's just the non-homogeneous system. They take it a step further and prove local controllability for the full nonlinear system.
Wow. So they finally circle back and tackle the original problem in all its complexity. Tell me more. How do they do it?
The key is to leverage the results they've already proven for the non-homogeneous system. Remember that the nonlinear system just means that the source term f is a function of the system's state, making things a lot more intertwined.
So it's like the wind gusts in our car analogy are now dependent on the car's position and speed. Talk about a challenging parking scenario.
Exactly. To handle this, they use a powerful mathematical tool, the Banach fixed point theorem.
Now that sounds familiar. Isn't that a technique for finding solutions to equations by repeatedly refining an initial guess?
You got it. They cleverly define an operator denoted by O that encapsulates the system's dynamics. They then carefully demonstrate that this operator satisfies the conditions required for the Banach fixed point theorem.
So they show that this operator, when applied repeatedly, will converge to a fixed point, which represents a solution to the controllability problem.
Precisely. They prove that this fixed point exists and corresponds to a solution to the nonlinear system that satisfies the desired control objective.
That's fantastic. So they successfully navigate through all these complex mathematical concepts: Bessel functions, eigenvalues, biorthogonal families, weighted spaces, iterative methods, and fixed point theorems to ultimately demonstrate the controllability of this challenging nonlinear system.
Yes. It's a testament to the power of rigorous mathematical analysis and creative problem solving.
I'm starting to feel like I could write a math textbook after this deep dive.
Well, maybe not quite yet. But hopefully you can see how these seemingly abstract mathematical tools can have very real and tangible implications for controlling complex systems in various fields.
Absolutely. This research gives me a newfound appreciation for the power of math to unlock the secrets of the universe. What I find especially intriguing is how they bridge the gap between the simplified linear system and the full nonlinear model.
That's a great point. It's a common strategy in scientific research. Start with a manageable approximation and gradually build toward a more complete understanding.
And in this case, they do it with such precision and rigor. It's truly inspiring. Now let's delve into some of the finer details of their approach. Remember that Kalman rank condition we touched upon earlier? It turns out to be crucial for establishing the controllability of the linear system.
Absolutely. The common rank condition is a cornerstone of control theory. It helps us determine whether we have enough levers to steer the system in any direction we want.
Yeah, it was that condition involving a matrix and its rank. Can you remind me how it connects to controllability?
Certainly. In simple terms, the Kalman rank condition checks if we have enough steering power to maneuver the system in any direction we need. It ensures that the control input can effectively influence all the relevant variables in the system. In this specific case, the condition requires the rank of a certain matrix formed by combining the control operator B and the coupling matrix A to be equal to 2.
Okay, so it's like checking if our car has enough steering capability to navigate any twists and turns in the road.
Precisely. Now, the paper focuses on a scenario where the coupling matrix A has 2 distinct eigenvalues, which simplifies the analysis. They also impose another crucial condition represented by equation 1.6.
That equation looked a bit intimidating with all those symbols. What does it actually mean in the context of this problem?
It essentially places restrictions on the relationship between the eigenvalues of the coupling matrix and the zeros of the Bessel functions. Remember that the Bessel functions are linked to the eigenvalues of the degenerate diffusion operator, which govern the system's inherent dynamics.
So this condition ensures that the control input doesn't clash with the system's natural behavior, like making sure our steering input doesn't conflict with the car's suspension.
Precisely. It's all about finding the right balance between the external control and the internal dynamics. If this condition is violated, the control input might not be effective in steering the system to the desired state.
I'm starting to appreciate the intricate interplay between all these mathematical concepts. It's like a delicate dance where each step has to be perfectly coordinated.
Exactly. Now, to actually construct the control function, the authors cleverly leverage the moment method, as we discussed before. They transform the controllability problem into a moment problem, which involves finding a function that satisfies a specific set of integral equations.
Right. Each equation represented a moment of the function, like a snapshot of its behavior. But how do they solve this moment problem? It seemed pretty abstract.
The key is to find a special family of functions called a biorthogonal family. These functions are specifically designed to have certain orthogonality relationships with the exponential functions that appear in the moment problem.
So it's like having a set of keys that perfectly fit the locks of the moment problem.
That's a great analogy. By using this biorthogonal family, they can decompose the moment problem into smaller solvable pieces. They prove a crucial theorem, Theorem 4.1, which guarantees the existence of such a biorthogonal family under certain conditions.
Okay, so they found the right tools to unlock the solution to the moment problem. But how does that lead back to a control function for the original system?
Well, the solution to the moment problem provides coefficients that can be used to construct a control function that steers the linear system to zero. They then show that this control function can be extended to control the non-homogeneous system as well by carefully choosing appropriate weights in the Lebesgue spaces we talked about earlier.
So they start with the linear system, find a control function using the moment method, and then adapt it to handle the added complexity of the non-homogeneous system.
Precisely. And the beauty of it is that they provide explicit estimates for the control cost, giving us a measure of the effort required to achieve controllability. These estimates show that the control cost depends exponentially on the time horizon and the parameters of the system.
So the longer we want to control the system and the more complex its dynamics, the more effort we need to put in.
Exactly. It's a fundamental trade-off in control theory.
This has been a truly insightful deep dive. We've gone from seemingly abstract mathematical concepts like Bessel functions and biorthogonal families to concrete applications in controlling complex systems.
And hopefully you can see how, even in the realm of advanced mathematics, there's a beauty and elegance to the way these ideas connect and build upon each other to solve real-world problems.
Absolutely. This paper is a testament to the power of human ingenuity and the endless possibilities that lie within the world of mathematics. It's amazing how they've woven together so many different mathematical concepts to solve this controllability problem.
Yeah.
But I'm curious, what are some of the specific details and challenges they faced in applying these techniques?
One of the key challenges lies in verifying that the Kelman rank condition is actually satisfied. Remember, this condition involves checking the rank of a matrix formed from the control operator B and the coupling matrix A.
Right.
Proving that this rank is indeed equal to 2 requires a careful analysis of the structure of these matrices.
So it's not just a simple calculation.
No, it's not. They need to dig into the properties of these matrices to ensure the condition holds.
Okay, and remember that equation 1.6 we discussed earlier?
Yes.
It's not just an arbitrary condition.
Right.
It plays a critical role in ensuring that the control input, which is applied at the boundary, can effectively propagate through the system and influence its behavior.
Exactly.
Right. It was about ensuring that the control input doesn't clash with the system's natural dynamics. It involved a relationship between the eigenvalues of the coupling matrix and the zeros of those Bessel functions.
Precisely. Verifying this condition involves a delicate interplay between linear algebra and the properties of Bessel functions. It requires demonstrating that certain determinants which capture the relationship between these mathematical objects are non-zero.
So it's like making sure all the gears in a complex machine are meshing correctly.
Exactly. Now let's talk about the moment method in more detail. It's a brilliant technique, but it also introduces its own set of complexities.
Okay.
Remember, the moment problem involves finding a function that satisfies a specific set of integral equations, each representing a moment of the system's behavior.
Right. It was like capturing those snapshots of the system at different times.
Precisely. To solve this moment problem, they need to construct a biorthogonal family of functions. These functions are special because they have specific orthogonality properties with respect to the exponential functions that appear in the integral equations.
Okay, so it's like finding the right set of keys to unlock the moment problem. But how do they actually go about constructing this biorthogonal family? It sounds quite challenging.
It is. They utilize a recursive process defining the functions in the biorthogonal family one by one, ensuring that each function satisfies the required orthogonality conditions. This involves a series of careful calculations and estimations, making sure that each step builds upon the previous one.
It's like building a delicate structure, brick by brick, making sure each brick is placed precisely to maintain the stability of the whole.
And the key to the success of this construction lies in Theorem 4.1. This theorem provides specific conditions that, when met, guarantee the existence of such a biorthogonal family. It's a crucial piece of the puzzle because without it, the entire moment method would fall apart.
So Theorem 4.1 is like the blueprint that guides the construction of the biorthogonal family, ensuring that it has the right properties to solve the moment problem.
Exactly. Once they have constructed the biorthogonal family, they can then use it to decompose the moment problem into smaller, more manageable pieces. It's like taking a complex musical score and breaking it down into individual instrument parts, making it easier to understand and perform.
And how does this decomposition of the moment problem help them find a control function for the original system?
The solution to the moment problem provides coefficients that can be combined with the functions in the biorthogonal family to construct a control function. This control function is tailored to steer the linearized system to zero, effectively achieving the desired control objective.
So it's like using the individual instrument parts to assemble a harmonious symphony of control.
Precisely. And remember, they started with a simplified linear system, but the real challenge lies in extending this control strategy to the more complex non-homogeneous system where there's an external source term disrupting the system's behavior.
Right? It was like adding those wind gusts to our car parking analogy, making the control task much harder.
To handle this, they introduce weighted Lebesgue spaces. These spaces allow them to assign different levels of importance to the source term at different points in time, effectively capturing its dynamic influence.
So it's like paying more attention to the strongest wind gusts, as those will have the biggest impact on our parking maneuvers.
Exactly. By carefully choosing these weights, they can fine-tune the control function to effectively counteract the disruptive effects of the source term. And what's remarkable is that they provide explicit estimates for the control cost, giving us a quantitative measure of how much effort is needed to achieve controllability.
So they don't just say it's possible to control the system, they give us a way to measure how difficult it will be.
Precisely.
Yeah.
They show that the control cost increases exponentially with the time horizon and the system's parameters. This means that the longer we want to control the system and the more complex its dynamics, the more effort we'll need to invest in our control strategy.
It's like saying that parking a car in a tight spot for a short time might be manageable, but trying to keep it perfectly parked there for hours on a windy day would require a lot more skill and effort.
Exactly. And what's even more impressive is that they go beyond the non-homogeneous system and ultimately prove local controllability for the full nonlinear system. This is the holy grail of control theory, demonstrating that with the right techniques we can tame even the most challenging and unpredictable systems.
It's a testament to the power of human ingenuity and the beauty of mathematical thinking. We started this deep dive with a seemingly abstract problem involving partial differential equations and Bessel functions, and we've ended up with a profound understanding of how to control complex systems in the real world.
And hopefully this journey has given you a glimpse into the fascinating world of mathematical research, where abstract concepts and rigorous analysis can lead to tangible solutions to real-world problems.
Absolutely. It's a reminder that math isn't just about equations and formulas. It's a powerful language that allows us to describe, understand, and ultimately control the world around us. Thanks for joining us on this incredible deep dive. We'll see you next time for another adventure into the world of knowledge. Welcome to another deep dive. Today we're tackling a pretty challenging topic, the controllability of a system of nonlinear, degenerate, parabolic equations. We've got some really dense research excerpts to go through, and trust me, this isn't your high school algebra, but don't worry. We're going to break it down piece by piece, focusing on all the fascinating math, really going to unpack these proofs in detail for you.
Yeah, we're going deep into the mathematical machinery behind this problem. You know, imagine if you could actually control something like heat flow or diffusion, even when that diffusion rate is uneven and can actually slow down or even completely stop in certain areas.
Yeah, so like imagine a frying pan, right? And some spots on that pan heat up way faster than others.
Exactly.
That's that degenerate part. And we're trying to control this kind of uneven heating process, but we're only allowed to apply a single control. And it can only be applied at the boundary of the system. So how do we even know if that's even possible?
Well, that's where this idea called Kalman's rank condition comes in. It's sort of like a gatekeeper. It tells us if a system even has the potential to be controllable at all. It basically looks at the control operator and the coupling matrix.
Okay, so we're checking if the way we're applying that control at the boundary, and then the way that those equations are kind of interacting internally, whether those two things together are actually enough to potentially control the entire system.
Exactly.
It's like making sure the steering wheel and the engine in the car are actually connected properly and have enough power to, actually control the movement.
Exactly. Now, let's actually dive into the research excerpt and see how they approach this problem.
Yeah, great. So what's the first base tell us about the system itself?
Well, they lay out the mathematical representation. It's a system of two degenerate parabolic equations. And it's represented by this equation, Yahweh x, 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 a, y.
Okay, I'm already lost. Can we break that down a little bit?
Sure. Think of yes as basically describing how the system changes over time.
Okay.
Then we have the term nex, which represents that degenerate diffusion we were talking about. So Eki controls how much that diffusion can vary from place to place. Then there's S, which is really capturing the interaction between the two equations, with A being this coupling matrix that dictates how they influence each other. And then lastly, we have Ekti, which represents any additional forces or external factors that might be acting on the system.
So we're basically seeing like a snapshot of how this system evolves, considering the uneven heating, those internal interactions, and even any external factors that are going on. That's pretty cool. But what about the control part? How is that actually represented mathematically?
Right. So the control is represented by YD1, include BV80. V is the control force that we're applying at that boundary. And B is the control operator that basically dictates how that force is injected into the system.
Okay, so we're applying a force at the boundary and seeing if we can use that to, drive the system to zero. But again, how do we even know if that's possible?
Well, that's where Kalman's rank condition comes in. It requires that the rank of the matrix BAB is equal to the number of equations in our system, which in this case is 2.
Right.
So if this condition is met, then the control force through B and the system's internal dynamics through A, they have the potential to actually control the whole system.
Got it. So it's like checking if the tools we have are actually powerful enough for the job.
Yeah, exactly.
Now, if Kalman's condition is satisfied, then what's the next step?
Well, then the researchers introduced what's called the moment method, developed by Fattorini and Russell. And this method essentially transforms the controllability problem into something called a moment problem. And that lets us use spectral analysis.
Spectral analysis. You mean studying those eigenvalues and eigenfunctions? Those building blocks of the system's behavior?
Precisely. The eigenvalues tell us the rates at which different parts of the system evolve, and the eigenfunctions describe the corresponding patterns, or shapes of those evolutions.
Right, right. So if we can understand those building blocks, then we might be able to figure out how to manipulate the system at the boundary to actually get to our desired outcome.
Exactly.
This is where it starts to get really interesting. Okay, so what's on the next page?
Well, on the next page, they start talking about Bessel functions. And these are special functions that appear in, various areas like physics and engineering. And they play a really crucial role in actually characterizing the eigenvalues of our system. They point out that the eigenvalues are directly related to the zeros of these Bessel functions.
Hold on. Bessel functions. Can we just take a step back for a second?
Sure.
What are they and why are they important here?
Well, imagine like the ripples in a pond after you throw a stone in. Bessel functions, in a way, they describe those ripples, but in a more abstract mathematical setting. They capture how waves propagate and interact. And in our case, they're essential for understanding how the heat or diffusion in our system actually behaves.
Okay, so the points where these ripples sort of vanish, those zeros, are actually determining the rates at which our system evolves.
Yes, that's right.
That's fascinating.
And those zeros are not just random. They actually possess a very specific structure and order, which is key to understanding and proving the controllability.
Okay, so we're not dealing with like random numbers here. There's an underlying pattern that we need to decipher. Okay, I'm starting to see how these pieces might be connecting. What's next?
Okay, so next they introduce something called biorthogonal families. These are really important for constructing that control function that we're looking for.
Biorthogonal families. I think I need a bit more explanation on that one.
Sure. Imagine you have a set of keys, and each key can only unlock one specific door. And no other key can open that same door. That's kind of analogous to biorthogonal families. They're pairs of mathematical objects that have this unique property, where when you combine them in a specific way, they basically cancel out everything except for the one specific component you're interested in.
Oh, okay. So it's like having a very specialized set of tools that allow us to really target very specific aspects of this system.
Exactly. And in this case, these biorthogonal families are actually constructed using the eigenfunctions that we were just talking about.
Right.
And they basically help us isolate specific parts of the system's behavior, which is what we can then manipulate with our control function.
So without these biorthogonal families, it would be pretty much impossible to actually achieve really precise control over the system.
That's right. Now, they go into how this moment method uses these bioorthogonal families to actually construct the control function.
Okay, I'm ready to see how all of this comes together.
Okay, so the moment method basically expresses the control function as a specific combination of these bioorthogonal families.
Oh.
And they're weighted by coefficients that are determined by, the system's initial state and what outcome we want to achieve.
So we're basically like tailoring a custom-made control function using these bioorthogonal families as our building blocks.
Yeah.
And we're kind of adjusting the amounts of each building block based on what we want the system to actually do.
Precisely. It's really a very ingenious approach that really utilizes, all the properties of these bioorthogonal families to achieve precise control.
I'm starting to see the elegance in this approach.
Yeah.
We've gone from what seemed like an impossible task to a very well-defined mathematical strategy.
Exactly. And it doesn't stop there.
Oh, no?
No. They then introduce this idea of control cost,
Okay.
which basically measures the effort or energy that's required to actually implement our control function.
Right, because controlling something in the real world usually requires, some kind of resource. So what are the factors that influence this control cost?
Well, they point out that it depends on things like the time horizon over which we want to control the system, and also the initial state of the system.
Okay.
So essentially, the further we want to steer the system and the more out of whack it is initially, the more effort it will take.
Right. Makes sense.
And they actually give a mathematical estimate for this cost, which has what's called an exponential dependence on time.
Exponential dependence. Doesn't that mean it could get, really costly really quickly?
It can, which is why finding efficient control strategies is so important, especially when you're dealing with longer time horizons.
Absolutely, yeah.
And to kind of refine this cost estimate and tailor it to this specific system, they introduce these functions, UF, ARIF, and ERS.
Okay, so Troy is kind of like a measure of the system's inherent controllability, or accounts for those external influences that might be acting on the system. And then Roy's is linked to the initial state and how much we want it to change. It's like we have this formula now.
Right.
That can actually calculate the effort based on, the system's properties, those external factors, and our starting point. So controlling a simple system is one thing, but what happens when we add those external factors in? Those Eckwarth terms we were talking about earlier.
Right. That's where the idea of controllability of the non-homogeneous system comes in.
It's like adding wind gusts to our frying pan analogy.
Exactly.
Right? It makes it a lot harder.
Suddenly, controlling that temperature becomes a lot more complicated.
Yeah, exactly. So how do they handle that?
Well, to tackle this more complex scenario, they introduced two new operators, C1, T, and E0. And they're specifically designed to kind of handle those additional forcing terms and still be able to guide the system towards zero.
So C1T is like our smart thermostat that's constantly adjusting based on, the temperature of the room and the weather outside.
Yeah.
And then E0T is kind of predicting how the room's temperature is going to change over time.
Great analogy. And then they go on to actually prove, some crucial properties of these operators, making sure they can achieve that desired controllability even for this non-homogeneous system.
This is getting pretty intense, but I love how they're systematically building up this toolkit, to tackle increasingly complex aspects of this problem.
Yeah.
Okay, so what's next?
Well, next, they present two clever methods for controlling this non-homogeneous system. They call them the iterative method and the fixed point strategy.
Two different approaches. So there's more than one way to solve this mathematical puzzle. Tell me more about this iterative method.
Well, it's kind of like, imagine tidying up a really messy room. Instead of trying to tackle everything at once, you focus on one area, then another, and so on. So the iterative method basically breaks the problem down into these smaller, manageable pieces, and you control each piece sequentially.
Divide and conquer. I like it. What about the fixed point strategy?
That one's a little more subtle. It aims to find a state where the system is in balance, even with those external forces acting on it.
Okay.
So imagine finding a stable equilibrium point where the system naturally wants to be.
Okay, so it's like we're finding that sweet spot where, even with the external forces pushing it around, the system kind of just settles there naturally.
Exactly. And once we find that sweet spot, controlling the system becomes a lot easier.
Okay, I like both of those. They both seem pretty ingenious. So how do they actually use them to actually solve our control problem?
Well, they leverage the fact that our parabolic equations are what's called dissipative, meaning that the system naturally tends to kind of settle down over time.
Okay.
So they're actually working with the system's natural tendencies
Smart.
to make the control process smoother.
That's very clever.
So the iterative method uses this dissipation to drive those uncontrolled parts towards zero after each step. And the fixed point strategy uses that stability to make sure that the system stays close to that desired equilibrium point, even with those external forces.
This is really impressive. They're not just forcing the system. They're working with its inherent dynamics.
Right.
That's really cool. Okay, so where do they go from here?
Now they actually focus on proving the local exact controllability of the nonlinear system.
Okay, can you remind me what local exact controllability actually means?
It means that we actually want to drive the system to exactly zero, not just close to it, but only within a certain neighborhood around zero.
Okay, so it's like having really precise control over the car's steering wheel.
Yeah.
But only within a certain range of motion.
Exactly.
Yeah.
So precise control, but within a limited scope. And to prove this, they actually employ the fixed point strategy. They define a specific mathematical operator denoted as O. And it maps those external forcing terms to themselves, but it does it using the controlled system's behavior.
So it's like a feedback loop. It takes the external forces, sees how the controlled system reacts, and then updates those forces based on that reaction.
Precisely.
Cool.
And the key to proving local exact controllability is showing that O is what's called a contraction mapping.
Right. A contraction mapping shrinks the distance between any 2 points that it's applied to.
Exactly.
So by repeatedly applying O, we're essentially squeezing those external forces and the system's response closer and closer together until they reach that sweet spot where everything's in balance and the system is at zero.
Exactly. And the researchers actually rigorously proved that O satisfies the conditions to be a contraction mapping, which guarantees that this shrinking process will actually happen.
Wow. They've built a mathematical machine that automatically guides the system to zero.
Yeah.
That's really cool. Okay, what's the final takeaway from this section then?
Well, they emphasize that this controllability depends on the initial state being close enough to zero and the external forces being appropriately bounded.
Okay, so we have this really precise control, but it comes with some limitations.
Right.
It's kind of like saying, we can steer the car perfectly, but only if we're already pretty close to our destination and the wind isn't blowing us too far off course.
Precisely. And so it underscores the limitations of local controllability, but it also highlights its power within those limitations.
Yeah, absolutely. This is amazing. We've already covered so much. Are you ready to dive even deeper?
Of course I am. I'm always ready for a deeper dive.
Okay, awesome. So what's next on the agenda?
Well, in the next section, we're going to go headfirst into the world of spectral analysis.
Okay.
Where those Bessel functions we talked about earlier are going to take center stage.
Okay.
We're going to see how they actually help us characterize the eigenvalues and eigenfunctions of the system, those building blocks of behavior.
Bring on the Bessel functions. What's the first step in this spectral analysis?
Well, the researchers start by laying out the mathematical framework for finding those eigenvalues and eigenfunctions of our degenerate diffusion operator, represented by Ceylin, and they introduce two really key parameters, kite and yun, which are going to play a really important role in all of this.
Parameters, what do they represent?
That basically describes how much the diffusion rate varies. How degenerate the system is.
Okay.
Hailing is actually tied to the order of the Bessel functions that'll show up in our solution.
Interesting.
They're kind of like the settings on our mathematical toolkit that we need to adjust based on the problem at hand.
Okay, so they're capturing those unique characteristics of the system.
Exactly.
And guiding our choice of the right mathematical tool.
Precisely. Now, to actually determine those eigenvalues and eigenfunctions, they present a set of equations that need to be solved. And you guessed it, Bessel functions play a crucial role in that solution.
I had a feeling those Bessel functions would be back. So how do they come into play here?
Well, the eigenvalues, which determine those system evolution rates, are directly tied to the zeros of these Bessel functions.
Oh, wow.
Specifically, the nth eigenvalue is given by Lanyong n Kidej to Minen, where Jian represents the nth zero of that Bessel function.
Okay, so those Bessel function zeros are like literally shaping the rates at which our system is actually evolving. Incredible.
It is. And they also provide this explicit formula for the eigenfunctions, which also involves those Bessel functions. And these eigenfunctions, together with the eigenvalues, actually form what's called a complete set, meaning we can use them to represent any function within our system.
Wow, so Bessel functions are like the main act here.
Yeah.
They're shaping the rates of evolution and the patterns themselves.
Precisely. And the researchers emphasize that these eigenfunctions form an orthonormal basis. So they're basically these building blocks that we can use to kind of break down complex functions into simpler components, which makes the whole analysis much more manageable.
It's like having a perfectly organized toolkit, where every tool has a very specific purpose, and they all work together perfectly.
Exactly. But there's even more to these eigenvalues than just their connection to those Bessel functions. The researchers actually point out this really crucial property called the gap condition.
Right.
And this makes sure that those eigenvalues are sufficiently spaced apart from each other.
Why is the spacing between the eigenvalues important?
Imagine, like, radio frequencies.
Okay.
If two stations are broadcasting on frequencies that are too close together, their signals are going to interfere.
Right. It'll be all garbled.
Yeah, you get a jumbled mess. Similarly, if our eigenvalues are too close together, the system's behavior becomes very difficult to analyze and control.
So the gap condition makes sure that each eigenvalue has its own distinct channel.
Exactly. It's like having, a well-organized radio dial where each station has its own clear frequency.
I like that analogy. Okay, so we need those well-spaced eigenvalues for a clear signal. What else do they say about the eigenvalues?
They also point out that the series formed by the reciprocals of the eigenvalues converges. Now, this might seem like a really technical detail, but it actually has really important implications for controllability.
How does the convergence of a series relate to controllability?
Well, think of it like having enough concentrated power to actually steer the system in the right direction. If that series diverged, it would mean that the energy is kind of spread out too thinly, making it much harder to influence the system.
Okay, so it's like having a strong focus beam of light versus a weak diffuse one.
Right.
That strong beam is going to be much more effective at, illuminating a specific target.
Exactly. So this convergence property assures us that the system is well suited for the control that we're aiming for.
Okay, so we've covered a lot of ground here with our spectral analysis.
Yes.
We've got those eigenvalues, the Bessel functions. Now that we've got a pretty good grasp of that scalar case, where do we go from here?
Well, next we actually tackle the spectral properties of those vectorial degenerate operators, L and L. These represent the entire system's dynamics. So we're taking into account those interactions between the two equations.
So we're going from looking at the individual instruments to now the whole orchestra.
Precisely.
Yeah.
And just like with the individual instruments, understanding the properties of these operators is crucial for being able to actually manipulate the whole system effectively.
Okay, I'm ready. Tell me about these vectorial operators.
So L and L, they combine that individual diffusion behavior of each equation, with those interactions dictated by that coupling matrix A, and it's a joint A. And you know what? The eigenvalues of L and L are actually closely related to the eigenvalues that we found for the scalar case.
So those Bessel function zeros are still the key players.
Absolutely.
Even in this more complex setting.
Yeah, they provide formulas for these eigenvalues that, again, involve the Bessel function zeros and the eigenvalues of that coupling matrix A. And then they also describe those corresponding eigenfunctions, which, as you might expect, also involve Bessel functions.
Now we're basically building off our understanding of that simpler scalar case.
Yeah.
And now we're using that as a stepping stone
Yeah.
to really tackle this more complicated vectorial setting.
Exactly. And the researchers highlight some crucial properties of these eigenfunctions, which are essential for our controllability goals. First, they show that the eigenfunctions of L and L actually form those biorthogonal families.
Those specialized keys are back. So they're going to help us construct our control function for this more complex system, right?
Exactly. They're going to be essential for that.
Okay, this is really exciting. So what other properties of these eigenfunctions do they talk about?
Well, they prove that these eigenfunctions actually form complete sequences in L2, 0, 1, 2. So basically that means they can represent any function in that space.
So they're really like versatile building blocks. And we can use them to construct any complex shape that we need, just like in the scalar case.
You got it. They also show that these eigenfunctions form biorthogonal Riese bases of L2, 0.
Riese bases, right. Those really well-behaved bases that we need to ensure those stable and accurate representations.
Yes. And lastly, they prove that one of those biorthogonal families forms a basis of H1, 1, 1, 2, while the other is a basis of its biorthogonal space in H1 on 1, 2.
Right, those weighted Sobolev spaces and their duals. What's the significance of this connection?
It highlights the duality between those spaces, which is really important for understanding how we can actually control the system using inputs. The biorthogonality between these families basically gives us the tools to target specific aspects of the system, even in this complex vectorial setting.
Wow, we have really gone deep into these mathematical foundations of the system.
We have.
Okay, what's next on our agenda?
Well, now that we have a very solid foundation, we can finally tackle that boundary controllability of the linear system. We'll see how all those tools that we've been talking about, those eigenvalues, eigenfunctions, and biorthogonal families, all come together to prove that we can actually drive the system to zero using just a control applied at the boundary.
This is what we've been building up to. What's the first step?
Well, they start by reminding us that the controllability of this whole system really hinges on understanding the solutions to what's called the adjoint system.
The adjoint system, that mirror image that's going backward in time. Can you just remind me why it's so relevant here?
Sure, it's like watching a film in reverse to understand how a particular scene was created. By studying how the solutions to that adjoint system behave, we actually get valuable insights into how to actually control our original system. So they basically establish this key link between the solution of our linear system and the solution of that adjoint system. And they present this integral formula that connects the two, and it involves our control function and that adjoint system solution.
Okay, so this integral formula is like a bridge, between the original system and its kind of like time-reversed counterpart. What kind of insights can we gain from this connection?
Well, it gives us a test for potential control functions. Basically, it tells us that we can find a control function that steers the original system to zero at a specific time, if and only if that control function satisfies a certain condition that's related to the adjoint system solution.
So it's like a filter.
Yeah.
That's going to help us identify the control functions that will actually work. But how do we use this test? Don't we need to know the adjoint system's solution first?
Right, and that's where those eigenfunctions that we talked about come back into play.
Ah, okay.
The researchers use the fact that the eigenfunctions of the adjoint operator form a basis.
Right.
And this allows us to express the solution of the adjoint system as a combination of those eigenfunctions.
Right, right. So we're breaking down this complex solution into these simpler components that we actually understand.
Exactly. And this is really key because it lets us plug the adjoint system's solution into that integral formula we were talking about.
Okay.
And when we do that, we get a specific condition that the control function must satisfy.
Okay, I'm starting to see how these pieces are fitting together. What does this condition actually look like, and how does it help us find that actual control function?
Well, the condition is a set of equations, and these equations actually involve integrals of the control function multiplied by exponential functions that are related to the eigenvalues of that adjoint system.
Okay.
And these equations are what's known as a moment problem.
Moment problems, we've seen those before.
Yeah.
It's kind of like trying to find a recipe.
Right.
That perfectly balances a set of like given ingredients.
Yeah.
But in this case, those ingredients are determined by the system's eigenvalues and eigenfunctions.
That's an excellent analogy.
Yeah.
And just like finding that right balance of ingredients is key to a successful recipe. Solving that moment problem is absolutely crucial for actually finding a control function that drives that system to zero.
Okay, I'm with you. Moment problems are important. But how do we solve them?
Well, that's where those biorthogonal families come back into play.
Oh, right.
Remember those specialized keys?
Yeah.
Each one unlocks only one door.
Exactly, yeah. It's like having this set of tools that are designed to isolate and manipulate those individual components.
That's right. And so the researchers use those biorthogonal families to actually construct a solution to that moment problem.
Okay.
And they act like those filters, allowing us to actually isolate those specific components of the moment problem and solve them, like one by one.
So each biorthogonal element is targeting like a specific moment
Yes.
in the problem, which enables us to, create a precise and efficient solution.
Precisely. And so they demonstrate that this solution, the one they construct using those biorthogonal families, actually satisfies all the conditions of that moment problem.
Amazing. They've brought together adjoint systems, moment problems, biorthogonal families to actually solve this really intricate problem.
It's really impressive. And then they go on to show that the solution to the moment problem, which represents our control function, belongs to the space L20, D, which basically means it's a well-behaved function with finite energy.
Okay, so this isn't just some abstract mathematical object, right?
Right.
It's a solution that we could actually implement in a real-world scenario.
Exactly. And they even give an estimate of that control cost, which measures the effort needed to actually implement it.
Right. And we said earlier that cost can grow exponentially with time,
Right.
but they're showing that it's still bounded by a formula that depends on the system's parameters and that initial state.
That's right.
So we have a handle on the effort required, even if it might be substantial. That's good to know.
It is. And so they wrap up this part by explicitly defining that control operator, C0T, which maps that initial state to the corresponding control function. So it's kind of like a recipe that tells us exactly how to build a control based on where the system starts.
And, of course, they show that this operator is bounded.
Right.
Which ensures that it's going to behave predictably.
Yeah.
And not cause any unexpected problems. So with this, well-defined control operator, they've made really good progress improving the boundary controllability of our linear system. But we still have to address that non-homogeneous case where those external forces are coming into play. So how do they approach that? How do they approach this non-homogeneous case where it's even more difficult?
Well, they use a strategy that kind of adapts this iterative method developed by Lebeau and Rubiano. And this method basically breaks the problem into a sequence of smaller, more manageable steps.
Oh, okay. So it's like the divide and conquer approach again, but now we're applying it to this non-homogeneous case.
Exactly. And the key is to use the dissipative nature of the system. So, its tendency to settle down over time. And so they define a sequence of time intervals, and they construct a control function that acts on the system during each of those intervals.
Okay. So it's like a series of well-timed nudges.
Yeah.
Guiding the system towards zero step by step.
Exactly.
And the system's, kind of natural tendency to settle down is helping that process, even when the control isn't being actively applied.
That's right. It's like having this self-correcting mechanism built into the process. And they demonstrate that this iterative method converges.
Okay.
Meaning that as we go through those steps, the controlled states get closer and closer to zero.
Okay, so we've got this guarantee that this method's actually going to work. Do they give us any idea of how quickly this convergence happens?
They do. They provide estimates for the convergence rate, which shows, how that system state approaches zero with each iteration. And to handle that non-homogeneous case, they introduce a new control operator, C1T, which takes into account both the initial state and those external forcing terms.
So it's like an upgraded version of that control operator.
Right.
That can actually deal with that added complexity of those external influences.
Exactly. And just like the previous operator, they show that the C1T is bounded, ensuring that predictable behavior.
Bounded operators, these seem to be crucial for ensuring everything's stable and predictable.
They are. They ensure that our control strategies won't lead to any wild, crazy behavior in the system.
Right. Okay. So we've covered so much: joint systems, moment problems, bi-orthogonal families, iterative methods. This is amazing.
Yeah. It's a testament to the power of math to help us understand these really complex systems and develop these strategies to control them.
I'm with you. I'm ready for the next challenge. So what's next on our deep dive?
Well, now we're going to dive into the heart of that nonlinear control problem. And we're going to be using something called the fixed point strategy to prove the local exact controllability of the system.
The fixed point strategy, I remember we mentioned that earlier. It's about finding that state of perfect balance.
Precisely. It's a really powerful tool for proving the existence of solutions to equations, especially those with nonlinear terms, like ours.
Right.
And they use this concept to actually show that there exists a control function that can drive that nonlinear system to precisely zero within a certain neighborhood of the origin.
Ah, right. Local exact controllability.
Exact.
Precise control within that limited region.
That's right. And to implement the fixed point strategy, they define a very specific operator. It's denoted as O, and it maps those forcing terms in our nonlinear system to themselves, using the controlled system's behavior.
Okay, so O is acting like another one of those feedback loops. It's taking those forcing terms, seeing how the control system is reacting, and then updating the forces based on that reaction.
Exactly. And the key here is to prove that O has this really special property. It's what's called a contraction mapping.
Right. Those contraction mappings, they shrink the distance between any 2 points that you apply them to.
That's right.
So by repeatedly applying O, we're basically squeezing those forcing terms and the system's response closer and closer together until they finally reach that sweet spot where everything balances out and the system reaches zero.
You got it. And by proving that O is that contraction mapping, they guarantee that it has a unique fixed point. And that fixed point actually represents that forcing term for which the controlled nonlinear system precisely reaches zero at the final time. And they demonstrate very carefully that O satisfies all the conditions for being a contraction mapping.
Wow. It's like they built a mathematical machine that guides that system towards that perfect zero state.
It is. It really showcases the power of mathematical reasoning. But it doesn't end there. They actually go even further, addressing a few technical details, just to ensure that the fixed point strategy will hold up under scrutiny. First, they very carefully select two parameters, P and Q. And these are used to define certain functions within the fixed point strategy. And they show that by choosing these parameters correctly, they can make sure that a specific function, 2 remains bounded.
Bounded functions, another recurring theme.
No.
Why is that boundedness so important here?
Well, it makes sure that that whole control process remains stable and predictable, even when we have those nonlinear terms present. Because if we had unbounded functions, they could lead to really unpredictable, erratic behavior. They might even grow infinitely large, which would be disastrous for our control strategy.
Right. So it's like setting limits on the car's steering wheel to prevent any, wild, uncontrollable movements. Boundedness is keeping everything in check.
Exactly. And next, they focus on proving two really crucial properties of O that are absolutely necessary for that fixed point strategy to actually work.
Okay, what are those crucial properties?
Well, first they show that O maps a specific set of functions to itself, and it's represented by what's called the closed ball bow.
The closed ball bow. Can you remind me what that represents?
Sure, it's basically a collection of functions that are all close to each other in a specific mathematical sense.
Okay.
So by showing that O maps this set to itself, they're demonstrating that our control strategy is keeping us within a certain safe zone.
Okay.
And that it's preventing the system from veering off course.
So we're staying within the boundaries, so to speak.
Precisely. The second crucial property is that O is a contraction mapping, that shrinking property we talked about.
Yeah.
And that guarantees that O has a unique fixed point. And to prove this, they use the boundedness of 2RF combined with some clever inequalities and estimates to show that the distance between any 2 points mapped by O actually shrinks.
So we've got that mathematical guarantee that we're getting closer and closer to our target.
That's right.
Zero state.
Exactly. And so by establishing these two properties, they've actually fulfilled all the requirements of a very powerful theorem. It's called the Banach fixed point theorem.
The Banach fixed point theorem.
Yeah.
That sounds pretty important.
It is. It basically states that if you have a complete metric space, in our case, the closed ball bow, and a contraction mapping on that space, which is our operator O.
Right.
Then a unique fixed point actually exists.
So we've got the complete space, the contraction mapping, and a really powerful theorem that guarantees us a solution.
Exactly.
Sounds like we're in good shape.
We are. And so that fixed point of O represents that forcing term for which the controlled nonlinear system reaches exactly zero at the final time.
So we've achieved our goal.
Yes.
Local, exact controllability.
We have.
We've got those nonlinear terms, but we can still steer the system to zero. Within a certain neighborhood, of course.
Exactly. But they don't stop there. They go on to address a few more remaining details. They point out that the solution that we got from the fixed point strategy belongs to the space H, and that's really necessary to ensure that that whole control process is well behaved, and that the final state is actually zero.
Okay, so it's like a final check to make sure that everything is in order.
Exactly. And they emphasize that this whole local exact controllability result only holds if that initial state is sufficiently close to zero, and those forcing terms are appropriately bounded.
Right, so precise control, but within certain limitations.
That's right.
Wow, we have covered so much in this deep dive. It's been quite the challenging journey.
It has.
But it's also been incredibly rewarding, all these intricate concepts and brilliant strategies.
It really highlights the power of mathematics to unveil the inner workings of these really complex systems and guide us towards being able to control them.
I'm feeling a little bit overwhelmed, but also just incredibly inspired by all of this.
That's the beauty of exploration, right?
Mm-hmm.
Pushing the boundaries of our understanding and really embracing those challenges.
I'm really excited to see what other mathematical adventures are waiting for us, in future deep dives.
Well, we still have one more part to this particular deep dive. We're going to be exploring the appendix. And in the appendix, the researchers give us even more detailed proofs and insights into some of the concepts that we've talked about today.
All right, bring it on. I'm ready for round 3.
Okay, so let's jump into that appendix where the researchers give us some more detailed proofs and insights. And they start by revisiting that well-posedness of the non-homogeneous linear system. But they're taking a slightly different approach this time, using what's called the transposition method.
Right. We talked about the transposition method before. Can you remind me how that works again?
Yeah, it's all about understanding solutions by looking at how they interact with solutions to the related adjoint system, that time-reversed mirror image that we talked about.
Right, right. So we're using this like mathematical mirror to really analyze the system's behavior.
Exactly. And make sure that the solution that we have is actually well-defined.
Okay, got it.
So this time they use the transposition method to define what it means to be a solution to that non-homogeneous linear system.
Yep.
They introduce this integral formula that basically involves testing the potential solution against solutions to that adjoint system.
So it's like setting up a test that the function has to pass.
Yeah.
In order to be considered a legitimate solution.
Exactly. And they demonstrate that this definition actually leads to a unique solution that behaves predictably and stays stable.
Always good to know we're dealing with well-behaved solutions.
Absolutely. And then they kind of dive into the specifics of that solution, showing that it belongs to, particular mathematical spaces and has certain regularity properties.
Can you remind me again why those details about mathematical spaces and regularity are so important?
Sure. It's about making sure that the solution actually has the right characteristics for the controllability problem we're dealing with. So the mathematical spaces tell us, the type of functions we're working with, while those regularity properties basically guarantee that the solution is smooth and well-behaved without any sudden jumps or, unpredictable behavior.
Right. So it's like making sure that our mathematical tools are the right ones for the job.
Exactly.
And that the results that we get are reliable and meaningful.
Precisely. And they prove these properties rigorously using, clever inequalities, estimates, and results from functional analysis.
Very impressive.
Yeah.
It's like, building a house with a solid foundation, making sure that every step is planned and executed carefully.
Yeah. And they don't stop there. They actually also explore a specific case where the initial condition for the second equation in our system has even higher regularity.
Even higher regularity. What does that mean, and what are the implications of that?
It basically means that the initial condition for that second equation is even smoother and better behaved than we initially assumed.
Yeah.
And this extra smoothness has this ripple effect, leading to enhanced regularity for the second component of the solution, meaning that it also becomes smoother over time.
So a smoother start leads to a smoother journey. I like that.
Exactly. And this enhanced regularity is really crucial for ensuring that those control strategies that we've been talking about will actually work as intended, especially when we're dealing with those complexities of the nonlinear system.
Okay, so we've gained a much deeper understanding of the well-posedness of this system.
Yeah.
And how those solutions actually behave. What's next in this appendix?
Well, now they shift their focus back to those spectral properties of the operators L and L.
Okay.
Those vectorial operators that encapsulate the entire system's behavior.
Okay, those operators are back. I'm remembering those bi-orthogonal family
Yes.
of eigenfunctions that are so important for controlling the system.
You're right on track. And they provide a really detailed proof of how those bi-orthogonal families actually emerge and why they're essential for that whole controllability.
Okay, I'm ready to dive into the world of bi-orthogonal families.
All right, so they remind us that the eigenfunctions of L and L can actually be expressed using those eigenfunctions from the scalar case,
Right.
combined with specific vectors related to that coupling matrix, A.
Right. So we're building on what we learned from that simpler case.
Exactly, and using that to tackle the more complex setting.
Perfect.
And using this representation, they demonstrate that those eigenfunctions of L and L actually form bi-orthogonal families.
Okay.
They kind of walk us through the calculations step by step, showing that the inner product of any two different eigenfunctions from those families is 0, while the inner product of an eigenfunction with itself is 1.
Right. It's like those specialized keys that we talked about.
Yeah.
Each one's designed to unlock only one specific door, providing that precise control.
That's a great analogy. And then they further prove that these bi-orthogonal families are actually complete sequences in L201, meaning that they can represent any function in that space.
So we can use them as these versatile building blocks, capable of constructing any complex function that we need within our system.
Exactly. And they take it a step further by proving that these families form bi-orthogonal Rise bases. of L2012.
Rise bases, right? Those well-behaved bases that give us those stable and accurate representations.
Yes, and they meticulously show that these biorthogonal families satisfy all the conditions to be those Rise bases.
Okay.
Really showing their commitment to mathematical rigor. And then finally, they demonstrate that one of these families forms a basis of H1012, while the other forms a basis in its dual space, H1012, which highlights that duality between the spaces, which is really important from understanding how we can manipulate the system with control inputs. So those biorthogonal families actually bridge those two spaces, giving us those tools we need to control both the system and its mirror image precisely.
Wow, this appendix has been packed with so much information, detailed proofs, and really fascinating insights.
It has.
I feel like we've really explored the depths of this problem.
We have. And it really is a testament to the power of math to explain the behavior of these complex systems and to give us strategies for controlling them. The researchers have really carefully laid out the foundation for controlling this nonlinear degenerate parabolic system.
It's been an incredible journey, full of challenging concepts and these really sophisticated techniques. But I feel like I have a much deeper appreciation now for the beauty of mathematical reasoning.
I agree. It's remarkable how these really abstract mathematical concepts can be applied to these real-world problems.
Absolutely. This whole deep dive has really opened my eyes to the potential that math has to really make an impact on our world.
Well said. And this brings us to the end of our deep dive into the controllability of this nonlinear degenerate parabolic system. We've really explored the problem in detail, unpacked those proofs, and discovered the power of these mathematical tools like those biorthogonal families, moment problems, and fixed point strategies.
It's been a challenge, but incredibly rewarding.
It has. So until our next deep dive, keep exploring, keep questioning, and keep that mathematical curiosity alive.
Exactly. And remember, even the most complex problems, we can tackle them. You know, the combination of creativity, rigor, and the right set of tools. Welcome back to the deep dive. Today, we're diving deep into degenerate parabolic systems and how to control them using a single boundary force. I got a fascinating research paper we're going to break down.
Yeah, definitely. This paper tackles a really tough problem.
It does.
But it uses some really neat mathematical tools. We're going to unpack all the concepts.
Like we always do.
Explain the proofs, and we'll talk about why this research is important.
Sounds good.
In the bigger picture.
So the paper focuses on a system of two equations. These are degenerate parabolic equations.
Right.
And there's just one boundary control force to try to control this whole system. Let's start with equation 1.1.
Okay.
Which kind of sets the stage for everything we're going to talk about.
Yeah, so equation 1.1 basically describes how the whole system behaves. You have two equations that are kind of linked together. They have these variables, y1 and y2, which represent the state of the system at any given time. The thing that makes these equations tricky is that they're degenerate. You see that in the diffusion coefficients represented by the function ax. What that means is that this function can actually become 0 at certain points, which basically means the diffusion can slow down, or it can even completely stop at those points.
So it can vary over the space of the problem.
Exactly. It's not like a normal diffusion equation where the solution just smoothly spreads out over time. This one has these points where things get a little weird. Now, the control force is VAT. And it's applied only at the boundary x1.
Right.
The goal is to find a control function, VAT, that can drive the entire system to a specific state, which in this case, we want to make it 0.
To 0 everywhere in the domain.
Right.
So you mentioned that these equations are degenerate. Can you elaborate on that a little bit more?
Sure. So in a typical parabolic equation, you have this diffusion term that smooths things out as time goes on. Think of heat spreading in a metal rod. But in these degenerate equations, when that diffusion coefficient AX goes to 0 at certain points, it's like the smoothing effect breaks down. The solution can change very quickly or even stay kind of bunched up near those degeneracy points.
Interesting.
It's like you're trying to spread butter on a piece of toast. But there are these spots where the butter just won't melt. It's hard to make everything smooth and even.
Yeah. I can imagine that would make controlling the system pretty hard.
Oh, absolutely. It's like trying to steer a car with a wonky steering wheel. You got to be super precise and clever about how you apply the control.
So the fact that they're using a single boundary control force to try to do this is pretty significant.
Yeah, for sure. Previous research, a lot of times they would rely on something called distributed control, which is basically like having multiple control points all over the place. It's kind of like having a bunch of steering wheels in a car. But in a lot of real-world applications, you can't do that. You can't just control the system everywhere.
Right.
Think about trying to regulate the temperature inside a complicated machine or controlling a chemical reaction in a small container.
Yeah, I see.
You only have access to certain points.
Okay.
So being able to control everything just from the boundary, that's a big deal.
Right.
It opens up all these new possibilities.
So this is a huge advance in the state of the art here.
Yeah.
Now, this paper dives into proving something called well-posedness. Can you tell us what that is and why it's so important?
Okay, so well-posedness just means that the system makes sense mathematically.
Okay.
It behaves in a predictable way. It has a unique solution given a set of initial conditions.
Right.
And this solution changes smoothly as you tweak those initial conditions. It's like saying if you start the system off in a slightly different state. Yeah.
You won't get a wildly different outcome.
Okay.
It's stable and predictable.
No chaotic behavior.
Exactly.
Yeah.
If a system isn't well posed, it's really hard to control because the tiniest change could throw everything off.
Makes sense.
Yeah.
The paper uses something called a solution by transposition to establish this well-posedness. Can you explain what that means?
Okay, solution by transposition is kind of like a roundabout way of solving things.
Okay.
Instead of directly tackling the original system, you look at its adjoint system.
Okay.
Which is like a mirror image of the original, but with time running in reverse.
Oh, that's interesting.
Yeah. So you study the solutions of this adjoint system, and it gives you clues about how the original system behaves. For our system, the adjoint system is described by equations 2.1 and 2.2. Notice how the time derivative has flipped signs and the boundary conditions have changed? By looking at this mirror image, we can learn a lot about the original system.
So it's like looking at the problem from a different perspective.
Yeah, exactly. Gain some insights.
It's like trying to understand a sculpture.
Yeah.
I might walk around it, look at it from different angles to get the full picture.
I see. And proposition 2.2 in the paper, that establishes the well-posedness of the linear version of this system, which is equation 1.8.
Yes, so proposition 2.2 is a key result. It shows that if we simplify things a bit and look at the linear version of the problem, everything behaves nicely, it's well posed, and this gives us a good starting point to tackle the more complicated nonlinear case later on.
All right, that makes sense. So let's move on to the spectral analysis. The paper introduces these things called Bessel functions.
Okay.
And their connection to the eigenvalues of something called the degenerate diffusion operator. Can you walk us through that?
Sure thing. So Bessel functions are like these special mathematical functions that pop up all over the place in science and engineering. They're really useful when you're dealing with things that have cylindrical or spherical shapes. In our case, they help us understand the spectrum of this degenerate operator.
Okay, now when you say spectrum, you mean the eigenvalues.
Exactly. Eigenvalues are these special values that tell you how the operator acts on certain functions. They kind of give you the fingerprint of the operator. They tell you what's unique about it.
So how do these Bessel functions come into play?
Well, the zeros of Bessel functions, the points where the function crosses the x-axis, those points are directly linked to the eigenvalues of the degenerate diffusion operator.
Oh, interesting.
It's spelled out in proposition 3.1 in the paper. This proposition gives us formulas for the eigenvalues and their corresponding eigenfunctions, which are built using Bessel functions.
So these abstract mathematical objects have a very real connection to this problem.
They do. And understanding those eigenvalues is super important for figuring out how to control the system. Lemma 3.2 highlights some key properties of the eigenvalues, like the gap condition and the fact that the reciprocals add up to something finite.
Okay, well, what is the gap condition?
So the gap condition basically means that the eigenvalues are spaced out nicely. They're not all clumped together. This spacing is crucial for control because it means you can kind of excite different parts of the system independently. Imagine trying to play a piano where all the keys are really close together.
Okay, yeah.
You wouldn't be able to hit individual notes. The gap condition ensures that we have that separation so we can control things precisely.
So the gap condition's like having well-spaced keys on a piano.
Exactly.
Allowing us to hit those individual notes and control things really well.
Right on. And the fact that the reciprocals of the eigenvalues add up to something finite, that's important for making sure the control effort doesn't blow up to infinity. It guarantees that we can actually control the system with a reasonable amount of energy.
Okay, now we're getting to some really interesting stuff here. So moving on, we see this equation 3.7, which introduces the operator L, which is
it's a bit more complex.
A little more complex than the scalar operator we talked about before.
Oh, right. So this operator L, it combines the degenerate diffusion operator with a coupling matrix A.
Okay.
And this matrix basically describes how the two variables y1 and y2 interact with each other. It captures how changes in one variable affect the other.
Okay, so they're coupled together in some way.
Yeah, they're not totally independent.
Right.
They influence each other. And just like before, we need to look at the adjoint operator, which is L.
Okay.
And it turns out L and L share the same eigenvalues, which is super helpful for our control analysis.
So it feels like everything hinges on understanding these eigenvalues.
Yeah, for sure. The eigenvalues hold the key to controlling the system.
Right. Now, there's this concept of biorthogonal families.
Okay.
What are those, and why are they important in this context?
So biorthogonal families are sets of functions that are orthogonal, but with respect to two different operators, L and L.
Okay.
They're kind of like two sets of puzzle pieces that fit together perfectly, but in two different ways.
Interesting.
And these biorthogonal families are super useful because they allow us to express the control function in a very convenient way. We can analyze its properties more easily. It's kind of like having the right tools to dismantle a complex machine.
So how are they used specifically for expressing the control function?
Proposition 3.3 shows us how to construct these biorthogonal families using the eigenfunctions of L and L.
Okay.
It's like using those puzzle pieces to build the control function.
I see.
And then we can break down the control force into different components, each one associated with the specific eigenvalue.
Right.
It's kind of like separating a musical chord into its individual notes, so you can analyze each note separately.
It's like breaking down a complex signal into its component frequency.
Exactly. And then Proposition 3.4 goes a step further and says these biorthogonal families, they form something called a res basis.
What does it mean to form a res basis?
It means that they're like a really good set of building blocks that you can use to represent any function in a certain space.
Okay.
It's like having a set of Legos that you can use to build anything you can imagine. The fact that they form a res basis ensures that our control function is well behaved.
Right.
And we can use it effectively to control the system.
Okay, that makes sense. So we've covered a lot of ground here. We've talked about these degenerate parabolic systems. The role of Bessel functions, and eigenvalues, and we've seen how these biorthogonal families play a crucial role. It feels like we've laid a solid foundation for understanding how to control these really complex systems.
Absolutely. We've gathered all the essential tools. Now in the next part, we'll see how all these pieces come together to actually solve the controllability problem head on.
Sounds good. I'm looking forward to it.
It's going to be exciting.
So last time we really dug into the details of degenerate parabolic systems. We talked about all sorts of things like Bessel functions, eigenvalues, and those biorthogonal families.
Yeah, we covered a lot of ground.
We did. Now I'm really curious to see how all that comes together when we actually try to control these systems.
Yeah, that's the exciting part, right? Actually figuring out how to make these things behave the way we want them to. And remember, this paper is focusing on controlling the system from a single point on the boundary.
Right, which is a really unique approach.
It is, and it's a lot harder than it sounds. But the authors do a fantastic job of using all the tools we talked about last time to pull it off.
I'm ready to see how they do it. So they start by focusing on the linear system.
Yeah, they look at equation 1.3, which is a simplified version of the full problem. It's like a warm-up exercise before tackling the nonlinear case.
Makes sense to start with the simpler case. So how do they even begin to approach the controllability problem for this linear system?
They use this really clever trick called transforming the controllability problem into a moment problem.
Okay, a moment problem.
Yeah, it's a way of connecting the control function to the solutions of the adjoint system. Remember the thing we talked about?
Oh, yeah, the mirror image problem.
Yeah.
I see how these different concepts are all connected.
Exactly. They all fit together. And Proposition 4.1 is really important here. It basically says that you can drive the solution of the linear system, equation 1.3, to 0 at time t if and only if the control function satisfies a specific integral equation.
An integral equation involving the adjoint system, right?
Right. So if we can understand the adjoint system, we can figure out how to manipulate the original system.
Okay, that makes sense. But how does this relate to a moment problem?
Well, that integral equation, that's the moment problem. It relates the moments of the control function to integrals of the solution to the adjoint system.
I think I'm starting to see the connection here. But how do we actually solve this moment problem? It still seems kind of abstract to me.
That's where those biorthogonal families we talked about last time come in. They're the key.
It's like having the right tool for the job.
Exactly. And luckily, we already have those tools. Theorem 4.1 from a previous study tells us exactly how to solve moment problems using biorthogonal families. It lays out some conditions the biorthogonal families need to meet. And the great thing is that our biorthogonal families, the ones we built from the eigenfunctions of L and L, they satisfy all those conditions.
So we're in good shape. We have what we need.
We do. So what we do is we express the solution of the adjoint system as a series using those biorthogonal families.
Okay.
It's kind of like writing a song as a combination of different notes. You break it down into its basic components.
And that lets us analyze the adjoint solution more easily.
Exactly. So we break it down, and then we plug that series expansion into the moment problem equation. And what pops out is an explicit formula for the control function v. It's equation 4.11 in the paper.
Wow, so we actually have a formula for the control function. That's awesome. But how do we know this solution is valid? Are there any restrictions?
Yeah, we have to make sure that the control function we get actually makes sense physically. We want to make sure it doesn't require an infinite amount of energy.
Right, we don't want to blow anything up.
Exactly. So mathematically, we want to make sure the control function is square integrable. It means that the energy required to apply the control is finite.
Makes sense.
And thankfully, because of all the cool properties we've talked about, properties of the eigenvalues and biorthogonal families, we can actually prove that the control function does meet that requirement. It's all laid out in those equations leading up to equation 4.11.
Okay, that's reassuring. So we found a control function that, at least in theory, can steer the linear system to 0. But the paper also mentions something called a control cost. What is that, and how do we calculate it?
The control cost. That's basically a measure of how much effort is needed to control the system. It's like figuring out how much fuel you need to drive a car a certain distance.
Okay, so lower control cost is better.
Right. Means we can achieve our goal more efficiently. And Theorem 1.1 gives us a way to estimate this control cost. The estimate depends on those eigenvalues we talked about earlier.
So all those Bessel functions we discussed, they actually play a role in determining how much effort it takes to control the system.
They do. It's all connected. The faster those eigenvalues decay, the lower the control cost. It's like having a car with good brakes. It can stop more quickly and efficiently.
So we've tackled the linear system. What's next?
Now we got to step things up a notch. The next step is to look at the null controllability of the non-homogeneous linear system.
Non-homogeneous, what does that mean?
It means we're adding a source term to the equation. It's like having an extra force acting on the system, like wind resistance on a car. It makes the control problem a bit trickier. It's equation 1.8 in the paper.
So we're adding another layer of complexity. Why is this step important?
Because the real world is messy. There are always external factors influencing things. So if we can figure out how to control the system, even when there are extra forces acting on it, then we're in a much better position to tackle the full nonlinear case.
Makes sense. So how does this paper deal with a non-homogeneous case?
It all comes down to Theorem 1.2. It states that under certain conditions on the source term, we can guarantee null controllability of the non-homogeneous system. There are these special control operators that make it happen.
Okay, control operators.
Yeah, they're like mathematical functions that take the initial data and the source term as input, and they spit out the control function as output. They do all the heavy lifting for us. They're called C1t and E0t in the paper.
So these operators basically tell us how to construct the control function that drives the system to 0, even with all those extra forces acting on it.
Exactly. And the proof of this theorem, it's pretty clever. They use this iterative method where they control parts of the system's trajectory at a time, and then they leverage the fact that parabolic equations tend to smooth things out over time.
So it's like a divide and conquer strategy.
Yeah, exactly. They break the problem into smaller chunks and then use the inherent smoothing properties of the equation to drive the solution to 0.
I like it. So now that we've handled the non-homogeneous case, we're ready for the ultimate challenge.
Right. The big boss, the nonlinear system. That's where we'll see how everything we've learned so far comes together in a really powerful way.
Right, so we've spent the last 2 parts laying the foundation. We've looked at the linear system, and then we tackled the non-homogeneous linear system.
Yeah, we've been building up to this.
Yeah, it's time for the main event.
Right.
The nonlinear system, equation 1.1, the big one.
This is where things get really interesting. The linear cases were a good starting point. They gave us some really helpful tools. But the nonlinearity throws a whole new wrench into the works. It adds a whole other layer of complexity.
So how do we even begin to approach controlling a nonlinear system like this?
Well, theorem 1.3 is where the magic happens.
Okay.
This theorem tells us that we can actually achieve local, exact controllability of the nonlinear system.
Hold on, you said exact controllability.
Uh-huh.
Didn't we already achieve that with the linear system? I thought we already got there.
You're right. We did achieve controllability with the linear system, but that was null controllability. We were able to drive the system to 0.
Right.
Exact controllability is a bit different. It means we can drive the system to any desired state, not just 0.
Okay, so it's a more powerful form of controllability.
Exactly.
We have more flexibility.
Much more flexibility, yeah.
So what does this theorem 1.3 actually say?
Okay, so it says that if the source term f and the initial data y0 meet certain conditions, then we can find a control that steers the nonlinear system exactly to where we want it to go.
I see. So there are some caveats. What are those conditions?
Well, the source term f has to satisfy this inequality in equation 1.9. Basically, it means that f can't grow too quickly as the solution y changes.
Okay, so it's like putting a limit on how wild the nonlinearity can get.
Exactly. We're keeping it tamed.
Right.
And then the initial data y0 has to be small enough. Equation 1.0 gives us a specific bound on how small it needs to be.
So we're starting from a place that's already relatively stable.
Right. If the initial state is too far from where we want to end up, the nonlinearity could make things too difficult to control.
So we're starting close and being careful with the source term.
Got it. Now, how do we actually prove this theorem? How do we show that this exact controllability is possible?
Well, we use a fixed point strategy again.
Okay, like we did for the non-homogeneous case.
Similar idea, but this time we're working in a different function space, the space H, right? H. I remember we talked about that briefly before.
This space is special because it contains functions that decay at a specific rate as time goes on.
Okay, so the solutions we're looking for, they have to approach the desired state in a controlled manner.
Exactly. They can't be oscillating wildly or anything like that. Now, the fixed point strategy involves setting up a special operator. We would call it O in the paper.
What does this operator do?
It takes a source term, f, and maps it to a new source term. Essentially, it captures how the nonlinearity affects the source term.
Okay, so it's like taking the original source term, running it through the nonlinearity, and seeing what comes out the other end.
Exactly. And if we can find a source term that doesn't change when we apply this operator O.
So it's like a source term that's immune to the nonlinearity.
Right. If we can find that, then we found a fixed point for the operator O, and that means we've solved the control problem.
But how do we know if such a fixed point exists?
That's where the Banach fixed point theorem comes in handy.
Okay, I've heard of that one.
It tells us that if the operator O meets certain conditions, then a fixed point is guaranteed to exist. Specifically, O needs to map a closed ball in a particular function space into itself, and it has to be a contraction mapping.
So we're basically checking if O is a well-behaved operator.
Yeah, we want to make sure it doesn't create chaos. And because of all those careful estimates we did earlier, and because of the conditions we put on the source term and initial data, we can show that O does indeed satisfy those conditions.
So the fixed point exists, which means we've found a control that works for the nonlinear system.
We have. And that control function will steer the system to our desired state, and the solution will evolve smoothly within the space H.
It's amazing to see how all these different pieces fit together. Bessel functions, biorthogonal families, weighting functions, fixed point theorems, it's all connected.
It really is remarkable. It shows the power and elegance of mathematical thinking. And the coolest part is that the implications of this research go way beyond this one specific problem.
Absolutely. Thinking about controlling chemical reactions, optimizing heat flow and complex materials, even understanding biological processes, there are so many potential applications.
It's really exciting to think about the possibilities. This deep dive has given us a glimpse into how powerful mathematical tools can be for solving complex problems and opening up new frontiers of knowledge.
It's been a fascinating journey. So to wrap things up, what's the key takeaway for our listeners today?
I'd say it's this. Even when faced with incredibly complex systems like nonlinear degenerate parabolic equations, mathematics provides the tools and the insights to find solutions. It might be a challenging journey, but the rewards are worth the effort. Keep exploring, keep questioning, and never stop diving deep into the world of knowledge.
Well said. That's a perfect note to end on. Thanks for joining us on this deep dive. Until next time. Welcome to the Deep Dive. Today we're going deep into the world of degenerate parabolic systems. We're looking at a paper called Controllability for a 2x2 nonlinear degenerate parabolic system via one boundary control force.
Oh, yeah. This one's fascinating.
Yeah, this paper really caught my eye. It's all about how to control these systems. They behave a bit differently than your average parabolic equation.
That's right.
And we're going to be looking at using just one boundary control force.
Yeah, that's a fun challenge. Imagine like you have these two interconnected processes. Think of them as like two rooms and their temperatures influence each other.
Okay.
And you're trying to control both temperatures. But you only have one thermostat.
Oh, interesting.
That's the essence of what this paper is looking at.
Okay, so let's dive right in. The authors start by talking about these degenerate parabolic equations. Can you explain what makes these equations degenerate, what makes them different, and why does that even matter?
Yeah, definitely. So in a typical parabolic equation, you have a term that represents diffusion. So think about how heat spreads out smoothly over time. But in degenerate parabolic equations, this diffusion, it can be a bit uneven. It can even vanish in certain regions. It's like having a material that conducts really well in some spots, but then it acts like an insulator in others.
Okay.
So this degeneracy, that's what makes these equations trickier to analyze, because the solutions can behave in unexpected ways.
I see. So it's like having a car with a wonky engine. It might move, but you're not really sure which way it's going to go.
Exactly.
Okay, so the paper focuses on this specific system of two equations. Equation 1.1.
Right.
Can you break down what each component of this equation represents?
Sure. So you have your state variables. These are y1 and y2.
Okay.
And they represent the quantities that you are trying to control. So like the temperatures in our two-room example.
Okay.
Then you have your control function. This is V, and this is like our thermostat. The force that we are manipulating. Then there's this degeneracy parameter.
Okay.
And this kind of dictates how strong the degeneracy is, essentially how wonky that diffusion is. You also have your initial condition, which is like the starting state of the system,
Right.
and a reaction term. It's F.
Okay.
And this captures any interactions or feedback between the two processes.
Gotcha. Okay, so we've got a system of equations. Now, the paper emphasizes a rank condition. That's equation 1.2.
Yeah.
And then the assumption that this coupling matrix A has two distinct eigenvalues. That's 1.5. Why are those conditions important?
Yeah, so the rank condition is really crucial. It ensures that our single control force can actually influence both of the variables, even though we are only applying it at one boundary point. So it's like making sure that your single thermostat can actually affect the temperature in both rooms.
Oh, okay.
Not just one. As for the distinct eigenvalues, they tell us about the inherent dynamics of the system. So like how it would evolve without any control.
Right.
Having distinct eigenvalues means that we have these two separate modes of behavior that we can hopefully manipulate.
That makes sense. Okay, now the authors then jump into analyzing a linearized version of this system, equation 1.3. Why analyze this simplified version first?
Nonlinear systems are notoriously difficult to handle directly.
Yeah.
So mathematicians, we often start by studying a linearized version, something that captures the essential behavior near a specific point. It's like if you zoom in on a curved surface up close, it kind of looks flat.
Right.
And we can use much simpler tools to analyze it.
Okay.
So the insights from that linear analysis then give us a stepping stone for tackling that full nonlinear system.
Okay, so it's like building a model airplane before you actually try to fly a real one.
Exactly.
Gotcha. Speaking of controllability, the paper mentions this thing called the Kalman rank condition, equation 1.2, and then theorem 1.1. What do these tell us about controlling the linear system?
Okay, so the Kalman rank condition is a powerful tool. It tells us whether we can steer all variables in a linear system using our available controls. In this case, it's actually the same as the rank condition we discussed earlier, which means if our single control can influence both variables, then we're in good shape to actually control this linear system.
So that's a good sign. What about theorem 1.1?
Okay, so Theorem 1.1 gives us the precise conditions that are needed for what's called null controllability,
Okay.
which is being able to drive the system to zero
Okay.
at a specific time. It states that we need that rank condition to hold. But there's also this really fascinating connection to the system's eigenvalues
Okay.
and something called Bessel functions.
Bessel functions. Those sound familiar. I've heard those before in other areas of math and physics. What role do they play here?
Yeah, they pop up a lot. Bessel functions often appear when you're describing things with radial symmetry, like waves spreading out from a central point. In this context, they're actually tied to the eigenfunctions of the degenerate diffusion operator. So the part of the equation that governs how things spread out unevenly.
Yeah.
The theorem essentially says that for us to have controllability, the control force has to resonate with the system's natural frequencies, which are determined by those Bessel functions.
So it's like pushing a swing at just the right moment to make it go higher.
Exactly.
Okay, so Theorem 1.1, that tells us we can control this linear system. But how do we actually find the control force? And how do we know how much effort it'll take?
Yeah, good question. That's where this thing called the moment method comes in. This is a really powerful technique.
Okay.
And it kind of transforms the controllability problem into a different kind of problem. It's called a moment problem.
Okay.
And these moment problems, they're often easier to solve because they leverage these special sets of functions called biorthogonal families. Think of them as keys that unlock the solution.
Oh, so the moment method is the key to finding the control force.
Exactly. And not only that, Theorem 1.1 also gives us an estimate for what's called the control cost.
Okay.
Which is the effort that's needed to actually steer the system. And it turns out that cost depends on the time horizon. The shorter the time we have to control the system, the more forceful our control needs to be.
That makes sense. It's like trying to stop a speeding train.
Exactly.
You need way more braking power if you have less time to stop.
Exactly.
Okay, so we've covered this linear system analysis in pretty good detail.
We have.
We've talked about how the rank condition, eigenvalues, Bessel functions, the moment method, and the concept of control cost. All these things come together.
It's a lot.
It is a lot.
We've got to bring it all together.
But the journey doesn't end here.
No, it doesn't.
We still have this nonlinear beast to tame.
Oh yeah, the fun's just starting.
This is where it gets really interesting. We're going to see how the authors tackle the full nonlinear system using an iterative method and something called the fixed point strategy. But we're going to have to save that exciting part for part 2 of our deep dive.
We are.
So, dear listener, buckle up.
Yes.
And join us for the next leg of our mathematical adventure.
It's going to be a wild ride. Welcome back to our deep dive into the world of degenerate parabolic equations and their controllability.
I'm excited to see how we tackle the full nonlinear system.
Yeah.
We left off talking about these iterative methods and the fixed point strategy. What are those? And how do they help us deal with nonlinearity?
Okay, so think of an iterative method, like you're making these successive approximations to reach a solution. So you start with an initial guess, and then you just refine it step by step until you get close enough to what you want.
Okay.
It's like adjusting a recipe. You tweak the ingredients little by little until you get the perfect flavor.
I like that. So where does the fixed point strategy fit into all of this?
So the fixed point strategy is a way to prove that this iterative process actually converges to a solution.
Okay.
So imagine you have like a map of a city and it has a point marked, you are here.
Okay.
A fixed point on that map would be a location that doesn't move when you fold the map in a specific way. So the fixed point strategy basically guarantees that our iterative process, when applied to a special function, it will eventually lead us to a point that stays put.
Okay.
A solution to our control problem.
That's a really cool way to visualize it. So how do the authors actually apply these strategies in the paper?
They start by looking at the controllability of this slightly modified system, equation 1.8. It includes this extra term representing an external disturbance. It's like if you were trying to control a car, but you're accounting for like wind gusts.
Oh, okay.
That might push you off course.
So it's adding another layer of complexity.
Yeah, exactly. So Theorem 1.2 addresses this scenario. It says that even with this disturbance, we can still achieve null controllability, which is driving the system to zero under certain conditions.
And those conditions are probably more stringent than for just a linear system.
Yeah, you're right. The theorem actually provides estimates for the control cost.
Okay.
You know, the effort needed to control the system.
Right.
And those estimates actually depend on the size of that disturbance. So the stronger those wind gusts, the harder you have to work to keep the car on track.
That makes sense. But how do they actually prove this theorem? It sounds pretty challenging.
Yeah, it involves a lot of clever techniques. So they divide the time interval into smaller segments,
Okay.
and then they control the system on each of those segments using the insights from the linear analysis, and then they carefully piece those solutions together.
Oh, wow.
It's like navigating a complex route by breaking it down into these smaller, more manageable legs.
So breaking down a difficult problem into smaller solvable pieces.
Exactly. And this segmented approach is really effective because it allows them to exploit the dissipative nature of these parabolic equations.
Okay.
So these equations describe systems that have this tendency to settle down over time, like a swinging pendulum eventually coming to rest because of friction. By strategically controlling the system over these short intervals, they can leverage that tendency to their advantage.
So it's like you're using the inherent properties of these equations to gain control.
Exactly. So this combination of the segmentation, the dissipation, and the insights from the linear system analysis, it all comes together to prove that null controllability for that disturbed system, paving the way for tackling the full nonlinear system.
Okay, we are finally ready to face the nonlinearity head-on.
Yes, we are.
How does Theorem 1.3 help us reach that final goal?
Okay, so Theorem 1.3 is like the culmination of everything that came before.
Okay.
It establishes this thing called local exact controllability of the full nonlinear system. Equation 1.1. So local here means that we can only control the system if it starts close enough to our target state. So think of it like being able to dock a spaceship if it's already within a certain range of the space station.
Okay, so we can't control it from any arbitrary starting point.
No, not necessarily. But the theorem tells us that there is a region around our target state where we can do it.
Okay, so how do they use this iterative method and fixed point strategy to prove the theorem?
So they create this special function that captures this iterative process of refining that control force.
Okay.
This function takes an input control, and based on the system's response, it spits out an output control that gets us a little bit closer to what we want.
Okay.
Then the fixed point strategy comes in to prove that this function actually has a fixed point, a control that when you input it, it gives you back the same control.
Gotcha.
And that fixed point represents the control force that will successfully steer that nonlinear system to zero.
Wow, that sounds really abstract.
Yeah, it is a bit.
How do they find this magical fixed point?
It involves choosing the right mathematical framework. It's called a function space.
Okay.
And then verifying that the conditions of a really powerful theorem called the Banach fixed point theorem are met.
Okay.
This theorem basically guarantees that a fixed point exists if certain properties hold for our function.
Okay.
So the authors meticulously demonstrate that all of those conditions are satisfied, ensuring that the iterative process will actually converge to the desired control.
So they're building a mathematical machine.
You could say that.
That takes a rough guess for the control, and then it keeps refining it.
Yeah.
And they've proven that eventually this machine will spit out the perfect control.
Exactly.
To steer the system.
Yes.
That's amazing. It shows how intuition and rigor in math kind of come together.
Definitely.
You start with an intuitive idea like iteratively refining our control. But then you have to use these powerful theorems and careful analysis to guarantee that the idea actually works.
Exactly. And it's amazing how they combined all these different tools. Bessel functions, moment problems, fixed point theorems. Really shows you the power of math to solve complex problems.
It does. What are some of the key takeaways for our listeners? What should they remember from this part of our deep dive?
I think the biggest thing is we saw that even these systems with wonky diffusion, they can be controlled
under the right circumstances.
Yes.
Yes.
Secondly, the interplay between the system's dynamics, like the eigenvalues and the Bessel functions, and the control force is crucial for controllability.
Gotcha. Okay.
And lastly, we saw how powerful these mathematical tools are, like the moment method and the fixed point strategy, you know, for tackling these really complex nonlinear problems.
Well, it's been a really enlightening journey so far.
It has.
But we're not quite done yet. There's one more crucial aspect of this paper that we need to discuss.
Oh, yeah.
The author's analysis of the control cost for the nonlinear system.
Yeah, we need to understand how much effort it actually takes to control these nonlinear systems.
Because we know we can control them, but how hard is it?
Exactly. And that's going to lead us to some really interesting results.
That sounds intriguing.
Yeah.
But we're going to save that discussion for the final part of our deep dive.
We are.
So stay tuned as we wrap up this fascinating exploration
yes.
of degenerate parabolic systems and their controllability.
Welcome back to the deep dive. We're at the final stage now. Degenerate parabolic systems.
Yeah, we've covered so much.
We have.
From analyzing that linear system to tackling the full nonlinear case.
Using all those
clever tools.
All those iterative methods and fixed point theorems.
Exactly.
Okay.
But like you said, there's one crucial aspect left.
Yeah, the control cost.
Right. We know we can control these systems, but how much effort does it take?
That's what we're going to uncover in this final part.
Let's do it.
Okay, so let's dive into those estimates. Where do the authors begin? So they start by examining the control cost for that non-homogeneous linear system.
Yeah.
You know, the one with that extra disturbance term?
Right.
Theorem 1.2 stated that we can still achieve that null controllability even with those disturbances. Well, the proof of that theorem also gives us estimates for the control cost in this scenario.
And what do those estimates tell us?
Okay, so they show that the control cost depends on two main things: the time horizon and the size of that disturbance.
Okay.
So as you might expect, the shorter the time we have to control the system,
Right.
the higher that cost is going to be.
Makes sense.
It's like trying to stop a speeding train.
The
The less time you have, the more forceful the braking has to be.
Right. Okay. What about the effect of the disturbance?
The control cost also increases with the size of the disturbance.
Right.
So the larger the disturbance, the more effort we need to use to counteract its effects.
Right.
It's like trying to maintain a steady course in a boat while you're battling big waves. The bigger the waves, the harder you have to work.
Okay. So the control cost for the disturbed linear system makes sense intuitively.
Right.
What about for the full nonlinear system? That's where it gets really interesting, right?
Absolutely. Analyzing the control cost for that nonlinear system, that's a lot more challenging.
Yeah.
But the authors do provide estimates
Okay.
using that iterative method and the fixed point strategy.
Okay.
Remember, those tools allowed us to prove that a control exists that can drive that nonlinear system to zero.
Right.
Well, they also let us actually quantify the cost of that control.
And what do the estimates reveal?
Okay, so they show that the control cost for that nonlinear system, it's really tied to how strong that nonlinearity is. The more nonlinear the system, the higher the cost of controlling it is.
Okay.
It's like trying to steer a car with a really sensitive steering wheel.
Oh.
Even tiny adjustments can lead to these big changes in direction.
Wow.
So you need to be more careful and more forceful with the control.
So the nonlinearity itself makes it harder to control.
Exactly. And this shows a big difference between linear and nonlinear systems.
Okay.
In linear systems, the cost is usually proportional to how far you are from the target state. But in nonlinear systems, it can grow much faster.
Oh, wow.
As you get further away.
Yeah.
So controlling those highly nonlinear systems, it can be a lot more expensive.
Right. So much more effort required.
Exactly.
Okay. So we've seen how the control cost depends on the time horizon,
Right.
the size of the disturbance, and the strength of the nonlinearity.
Yeah.
Are there any other factors that play a role?
Yeah, the control cost also depends on the parameters of the system,
Okay.
like that degeneracy parameter and the eigenvalues of that coupling matrix.
Right.
These parameters, they dictate the inherent dynamics of the system, and that influences how hard it is to control.
So understanding all these different factors together, the time, the disturbance, the nonlinearity, and the parameters, it's all crucial
It is.
for effectively controlling these degenerate parabolic systems.
Exactly. And those insights that we get from these control cost estimates,
They can help us design control strategies that minimize how much effort we need.
Oh, that's cool.
Like, for example, if we have some flexibility with how much time we have,
Yeah.
we might want to choose a longer time frame to reduce that cost.
Oh, okay.
Or if we can change the parameters of the system,
Okay.
we might be able to reduce the nonlinearity or adjust those eigenvalues to make it easier to control.
So these cost estimates actually give us some practical guidance.
They do.
That's really cool.
And it shows how important it is to understand not just if a system can be controlled, but also how much effort it takes.
All right. That makes sense.
This can really help us design better control strategies for all kinds of applications.
Yeah.
From engineering systems to biological processes.
Well, this has been a really fascinating deep dive
Yes,
into these degenerate parabolic systems and how we can control them.
definitely.
We started with these basic concepts of degeneracy and diffusion.
Right.
And then we explored all these sophisticated mathematical tools.
Like that moment method and the fixed point strategy.
It's been quite a journey.
It has. And we've seen how these concepts help us not only understand controllability in theory, but also give us practical insights into the challenges involved.
Absolutely. I hope our listeners have a new appreciation for math.
Me too.
And how it can help us solve real problems.
This paper really shows how creative mathematicians can be.
It does.
In developing these elegant solutions for difficult control problems.
And it shows how these different mathematical concepts are all connected.
They are.
You know, from those Bessel functions to fixed point theorems.
Right.
And we can use them all together to solve these problems.
That's amazing. Well, to our listeners,
yes,
we encourage you to explore further.
Keep learning.
Delve into this paper.
Yes.
And maybe even go on some mathematical adventures of your own.
In the world of control theory.
Until next time.
Happy exploring.
Happy exploring.